Good. I think we can slowly start with the second part of the conference. My name is Patrick Reumerman from BTG in the Netherlands. I'm the coordinator of BioFit, and I would like to welcome you to the second part of the final conference of BioFit. I'm now sharing my screen, and I hope it works. Usually it does.
It's working.
Great, thank you. Yes, the meeting will be recorded. So if you do not want to be recorded, you can choose not to speak. Yeah, we think this is useful to do this. The second part of the conference, we had a first part, so I will give another introduction to the BioFit project. And because there are many people who have seen the first part, I will give essentially the same presentation, but try to give some different accents so as to keep it interesting for everybody. I will tell about the BioFit project, our overall objectives, our partnership, the retrofit mapping that we did, the flagship work we did on the case studies, and other BioFit activities, and I will tell something about the agenda for today. This picture is quite nice. It is of one of the case studies. The Astrocell Hallein company in Austria has implemented a 35 million liter second generation bioethanol production plant. It produces 1% of Austria's gasoline demand. We very much hoped to have visited this because it is a part of the project. Sadly, because of COVID, we had to do it virtually, but even then it was an impressive sight to see what happened there. And I'm quite sure that we will see more of it today. Well, BioFit, it's about the importance of bioenergy for the energy production and consumption in the European Union. About 58% of the renewable energy consumed in the EU is renewable. Yesterday we heard from the Bioenergy Europe presentation that also in 2019 it's more or less the same. So it continues to be important. Also, that is the idea of the IEA, which said so in their technology roadmap. And it is also not considered a transitional fuel by the EU, but it is here to stay. Interesting, what we saw yesterday was that the framework conditions are a very important part of the whole implementation. One of the case studies, Flumio Santo in Sicily. At the start of the project, it was considered to be a good case study. And during our project implementation, the framework conditions changed. And it turns out that it's for now not possible anymore. So yeah, we see they very much impact what we do. And it changes our work when it changes. Bioenergy retrofitting is used to replace fossil fuels or upgrade outdated renewable technologies. And if you don't put in a greenfield plant, a whole new greenfield plant, but only replace part of the installation, which is retrofitting, it generally helps because it lowers capital expenditure, decreases lead time, leads to faster implementation, less production time loss, and lower risks. So our overall objective is to facilitate the introduction of bioenergy retrofitting in 5 sectors: first generation biofuels, pulp and paper, fossil refineries, fossil-fired power, and combined heat and power. And the overall goal is, of course, to increase the share of renewable energy in the EU final energy consumption. We did this with 14 partners. Our project lasted a little bit more than 3 years. We are now near the end of the project. Yesterday, we had case studies in France, Italy, Greece, and Bosnia-Herzegovina. And now we go to all different countries. We go to Sweden, Finland, Austria, and Spain. Yeah, so we span many countries in Europe. Not all, that's too much, but quite a lot of countries are featured there. What we did was a number of mapping exercises to show that how many successful examples of bioenergy retrofitting. We made very nice fact sheets. We made sectoral recommendation papers. We made a very nice handbook which shows in detail what are the various options for bioenergy retrofitting, and we will have soon a set of digital support tools available on the website. This is the flagship of our project. We have developed 10 case studies together with market parties that are working in the field and are looking to decarbonize their operations. Yesterday, we worked on the right part of this graph. So it was on fossil refineries, fossil-fired power and CHP. You can say that is really the part where fossil energy is prevalent and bioenergy is more or less new. And the other characteristic of what we do today is that we go to the left part, the conversion of 1G biofuels plants and pulp and paper plants. And that can be characterized as sectors where bioenergy is already very prevalent or nearly dominant. And now you see that outdated renewable energy equipment replacement is the topic, or optimization of sectors where bioenergy is already a very big part of the day-to-day operations. Yesterday I already said what you can say in general about all this case study is that there are a large variety of technological options for high value added bioenergy products. So not only heat and electricity, but advanced biofuels, intermediate bioenergy carriers, etc., etc. Nearly all case studies result in an economically feasible project, and retrofitting results in a significant capex reduction compared to a greenfield plant of around 50 to 85%. We evaluated framework conditions. That was sometimes a bit difficult because these framework conditions are changing and have changed during the course of our project. And we saw that yesterday in the presentation of Bioenergy Europe. And of course, we try to also give advice to policymakers. Tomorrow, we have a policy breakfast where we will give our view on the things which needs to be done to increase the share of renewable energy from bioenergy in Europe. We have done a lot of meetings to inform, support, and have dialogue with industry. Besides industry fora, we have had also 2 virtual business missions. And they are virtual because of COVID. One of them was to Brazil, and the other one was to the Ukraine. Today, we have 2 sessions. The first session is roughly 1.5 hours. It is about pulp and paper. We will talk about the carbonization of pulp in the wastewater sludge. So it's typical an optimization project. And the other one was the production of second-generation biofuels at Oostercel Halijn. And you will see more of the thing which I showed you the picture of earlier in the presentation. Then we will have a short break and we will go to the second part of the conference. It's about 1G biofuels. We will talk about the Biocarburantes de Castilla y León 1G plant in Spain. And we will talk about one of the ways to produce jet fuel from biomass. This is, of course, a very hot topic. And one of the ways to do that is via the alcohol to jet process. So Swedish Biofuels will give a presentation on that. I wish you all a fruitful conference, and I hope we learn something with each other. And yeah, it's we are interested to see what comes next. So thank you all, and I would like to give the word to Heidi, I think.
Yes. Hello, I'm Heidi Saastamoinen from VTT Technical Research Center, and I have had privilege in being a sector expert in this project for pulp and paper sector. And I'm moderating this session today. It starts with 5 presentations from the sector related to bioenergy retrofitting, and afterwards we have half an hour slot for questions and answers. So first, I would like to give the floor to Professor Christian Merlin from Lund University, who also has worked in this project, and he will present the bioenergy retrofitting options in pulp and paper sector. Floor is yours, Christian.
Okay, thank you, Heidi. I will share my screen from here. I hope you can see it, and let's go to the presentation. Let's put full screen mode. Can you see my presentation and hear me?
Yes.
Yes.
Okay, very good. So as Heidi said, I worked also in this BioFit project while in my previous job at VTT. It was a pleasure to work in this project, and I will give an overview about the retrofits in pulp and paper sector. So first of all, so why is it interesting to look at pulp and paper sector? Well, one reason is that the pulp and paper industry plants, they both need but also produce typically a large amount of heat and power. And now it depends the situation, how is the balance between consumption and production? It depends a lot because, for example, these chemical pulp mills, for example, kraft pulp mills, there is even today a very small amount or quite small amount of fossil fuel is needed, or it could be even so that as in the new plants that no fossil fuel at all is needed, and there is also usually an excess of bioenergy produced. But then in some other mills, for example, in Central Europe, where they recycle paper, so there is like still quite a lot of external fossil fuel is needed, and we focused more in the projects of this first ones also because there is more possibilities with bioenergy retrofitting. In the second case, maybe different technology like heat pumps could be more interesting. And okay, one other aspect is of course that a huge amount of wood is used in this pulp and paper industry. So it means that even if we take some smaller streams for there, they will still could have a big impact if we want to produce more bioenergy, biofuels, or other bioproducts, or to substitute the fossil fuels produced there. And one thing is that maybe it's not so much related with retrofitting and so on, but okay, both in the collection chain of the raw materials here, when we are in the forest, we then take the bigger part for the pulpwood, the pulp and paper industry, but already in that phase we get a lot of these byproducts, for example, harvesting residues that we can use for bioenergy purposes. Of course, then at the plant we also get then a lot of byproduct, especially at the chemical pulping mill, for example, the bark and black liquor. Okay, but let's go on. Let's checking the time. So then about something about the drivers and barriers for pulp and paper industry retrofits. So why some drivers are that okay, especially the chemical pulp mills. So already today produce a lot of bioenergy, all the time we have this development that the mills are getting more energy efficient, so there is a bigger and bigger possibilities to produce also something else than just the energy and for the plant. More bioenergy or then additional products like biofuels or bioproducts. And also another development is that at least in Finland there was earlier so that the pulp and paper mills, they were located next to each other, but the new mills, for example Äänekoski, it's so there that the paper is produced somewhere else, so it means that there is a lot more than possibilities to produce some additional products or bioenergy. And okay, of course we have also then this global trend that the newsprint paper production is decreasing, so there is a need to produce also other products besides paper and cardboard, and that could be done through this bioenergy retrofits. And I heard a famous expert that some of you may know, also Ali Harlin. So he said that even though the cardboard production is increasing, so that still doesn't make up all the decrease in the newsprint production. So there is really need for new products. Then another aspect is this climate mitigation and targets for advanced biofuels in EU. And of course, one other thing is that they also talk about nowadays that if you don't use any fossil fuels in the mills and then extract some lignite, you could even then go even carbon negative in the pulp mills. So that is one thing. And yeah, and also that this to use these byproducts either then from the industry or then from the collecting chain, they are more sustainable than if you have to cut this especially slow growing forest from the biomass. Then some barriers. So of course, if we speak about those mills in Central Europe that use recycled paper, they don't have access to biomass residues. And also one important aspect to keep in mind is that, okay, for example, the sodium and sulfur balance at the mill. So some streams, for example, black liquor, they contain this kind of chemicals that need to be recycled almost completely back to the mill. Otherwise, it will not be attractive for the industry. And of course, the most part of this heat and power that is produced at the mill, it's used by the own process. Let's then go on. And then let's go more into the details about the different processes, because this really affects what can be done and what cannot be done. So first we have this mechanical pulping. How it basically works is that we have, for example, we can have a stone or something that is rotating, and we grind the wood into fibers, and actually the main part of this wood ends up there in the fibers. So on the small parts is going, for example, to liquid if there is a product, some liquid is produced. So there is not much possibilities to do this bioenergy retrofits. Then in this semi-chemical pulpings, where we do this chemical pre-treatment, there is already more, because more wood is dissolved already, when there are more possibilities to do this bioenergy retrofit. For example, biogas could be produced from the liquids, or then like this biocoal or hydrochar from wastewater treatment sludge from the liquid, and then there's most possibilities in this chemical pulping mills. For example, if we have the sulfate pulp mills, where the cooking chemical is sodium hydroxide and sodium sulfide. So here are different streams. I illustrate on the next slide more in detail those, but there is the black liquor and bark and so on. And then there is the different type, the sulfite pulp mills. The sulfite pulp mills are more common today. And these have totally different possibilities, the sulfite and sulfite kraft pulp mills. Good. So let's then consider first these kraft pulp mills, which are the most common mills, at least up here in the north, but I think also in the world. So how this process basically works? So it's so that we basically cook wood chips in the pulping steps, and what happens is that some part of the wood dissolves in this liquid called black liquor here. So in this case, it's mostly some part of the hemicellulose and lignin that goes here, and the sugars are actually degraded, so it's not possible to make any kind of fermentation after the pulping step from them. And then, okay, the pulp is basically bleached, and then if the paper plant is at the same site, there is a product or cardboard production, so then the cardboard is produced. But then for what is interesting for the retrofit is the byproducts. So here, this liquid after pulping, it contains quite a lot of water, up to 85%. But already when we concentrate it by evaporation, we get some streams that can be utilized. For example, one thing is this from the evaporator condensate, we get this methanol, and I will explain a little bit more in detail about that later. Small amount of methanol, and then okay, the black liquor. Even there is one other product that can be separated is crude tall oil, and that can be turned into biofuels. And then the black liquor itself can also be converted into biofuels via gasification or hydrothermal liquefaction. But one other thing that you can do is also then to extract lignin from black liquor and use that lignin for material or biofuels. And the only place where fossil fuel is currently used, if it's used at all, is then in the lime kiln in this type of mills. And here there has been a lot of options lately that some bioproduct, biogas, or then gas from bark gasification can be used to substitute that fossil fuel here in the lime kiln. We will hear more about this today about the bark gasification in Joutseno plant. And of course, there is also then a production of wastewater at the mill, and there is typically this activated sludge wastewater treatment process, but there could be also like biogas production from this sludge, and another option that we will hear and was studied also as a case in this project is the hydrothermal carbonization, so turning that into biocoal or hydrochar. Then, okay, if we look then this status of this retrofit options today, so we have to keep in mind that they have different technical readiness levels, these options. Some of them are already commercial, whereas some are still in the demonstration phase or pilot phase, or even at a lower technical readiness level. So what is commercial today is this biogas production from this mill wastewater treatment. For example, in the Äänekoski, there is production of biogas, and I think nowadays this belongs also to the Metsä Fibre, and this part. And then there is gasification of bark, what we will hear about today, already practiced in two mills in Finland by Metsä Fibre. Then there is lignin extraction from black liquor, for example, the lignoboost process in Sunila in Kotka by Stora Enso, or then the Domtar in the USA. There are also other processes than lignoboost for extraction of this lignin. I think that there is this lignoforce, and Andritz also has this A+ lignin. And then there is also biofuel production from crude tall oil. Maybe a famous example is this UPM biorefinery in Lappeenranta, but also in northern part of Sweden there is sun pine. I think that was this, in Piteå. What is then under demonstration? So basically what we will hear today about is this biocoal production from mill wastewater treatment sludge. There is a demo plant in Heinola by Sea Green, and then also this transportation fuel production from lignin, the Renfuel. They modify the lignin, and then they can co-feed it to oil refinery sun carbon. I don't know, should that be called a demo plant or pilot plant, but that has already, they have also development to separate lignin from black liquor and then produce the transportation fuel from that. And then there is the methanol production from black liquor evaporated condensate. This used to smell very bad traditionally, but I think technology by Andritz and which is demonstrated in Södra in Münster also, they have found a way to purify this so it can be used. And then there is also gasification of black liquor has also been demonstrated in PTO to produce methanol and dimethyl ether. Unfortunately, this was not so has not been uptaken so much by industry. Maybe it's quite because it's of course not so easy to replace totally the recovering boiler. So maybe that is one reason. Very interesting project going on, EU project running currently, this BL2F, and there this hydrothermal liquefaction of black liquor is being investigated. So you can make this convert part of the black to this biocrude by hydrothermal liquefaction, and then you could convert that oil further into ship and for example aviation fuels. There are also other development in the hydrothermal liquefaction by Steeper Energy in Norway and also I think Risela in Canada, but as far as I know, I think the raw material is wood residues and not like black liquor there. Okay, then quickly let's see about the sulfite mill. The situation is different. I go this through more quickly. So then here the situation is quite different compared to the kraft pulp mills. So here actually after pulping we can in the brown liquor we even have fermentable sugars which are produced from the hemicelluloses, and they can be actually turned into ethanol or biogas. And one other aspect or process that has been studied, at least conceptually, I don't know has this been demonstrated in any larger scale, so is the gasification of the brown liquor. Let's go to the next slide. So just some examples of these. So for example, this biogas production, it has been already run at other plants. So, but for example, Austrocell, which we hear more about today, so they have produced biogas earlier, and then retrofitting this to bioethanol production is studied as a case study, what we will hear more about. And ethanol has been also produced as the Borregaard plant, which is also as far as I know, old sulfite type of mill. And yeah, I could also mention that during the summer I visited this Metsä or in Manta there was this museum, and there was also a sulfite pulp mill there, and they also mentioned the option there that they have produced bioethanol there, but also they had some development to produce protein, this specular protein there in the museum, but this has been closed down, the facility nowadays. Then to the summary slide. So finally, this is retrofitting in pulp and paper mills is interesting because there are so big volumes. So even if we use a smaller side stream, it will have a large effect. And then, what kind of retrofit options we have? It really depends on the type of pulping process. Is it chemical, semi-chemical, or mechanical? And is it sulfate or sulfite process? And also that if there is like fossil fuels are still used at the mill or not. If they are not, of course, if there's still use of fossil fuel at the mill, it makes first sense to replace those with some of the byproducts, and only after that then look at the options to produce additional bioproducts or chemicals. And I mentioned already the different technical readiness level of the different mills, and in addition, finally, we have these options today, but there are also new developments in the field. If we, for example, in Finland, there are also not only the traditional dissolving pulp like production processes, but there is also new process, for example, based on ionic liquids, which are being developed in the pilot phase, and there is also some development for produce microcrystalline cellulose. So from these processes, there might become new streams which could also give like new opportunities to do also this bioenergy retrofit. For example, produce more biogas or some other, for example, ethanol from those those streams. So I think that was more or less it. I think hopefully I kept the time, and so I just want to thank. It was a pleasure to work in this project, and special thanks to Heidi Saastamoinen and Elina Mäki from VTT. And you can, if in case you have questions, also of course I will stay for the questions, but also you can you find my email address. So if you have some questions, so please contact me. Thanks.
Thank you very much, Christian, for this interesting presentation. Next, we go to park gasification and method. We had park gasification as a best practice in the project, and now we have development manager from Metsä, Pertti Lehmonen, to present their insights.
Hello, everybody. I tried to share my screen here, and let's hope that it's working. So my presentation is how to implement bioenergy in the existing industrial applications in the Joutseno gasification plant, and I also take an opportunity to discuss a little bit about the Äänekoski gasification. I start with our targets in terms of the. I will put the presentation mode. It might be better. I will share our sustainability targets in the Metsä Fibre. Give you the few words about the gasification process itself. Then we can go deeper in the Joutseno and Äänekoski park gasification plants, and then the experience about the gasification processes. So we are aiming as a Metsä Fibre to the fossil-free operations, and one part of this fossil-free operations is to reduce the fuel consumption or replace the fuel consumption in the lime kilns. That is the last and might be the hardest part to go to the fossil-free production in the pulp mill. And our roadmap to the fossil-free production is that we are aiming at the end of the. Now I lost the pointer somehow. Oh, it's here. We are aiming to the 2030 to be the totally fossil-free, and these lime kilns are the last remaining processes that are consuming fossil fuels. And we have two lime kilns that are already operating without the with the non-fossil fuels, and we are building new pulp mill in the Kemi, and then new Kemi mill will have the bark product gas as a fuel in the lime kiln. And we are studying in the Rauma what to do about the existing Rauma pulp mill. We are building in the Rauma the new sawmill. So we are quite confident that we can aim this, we can reach this target in the end of the decade. Few words about the gasification and its vital properties. In the lime kiln, we are producing the flame, and we need to have the certain temperature of the flame to be so that we can operate the kiln. And that is the reason that we have to have the dry fuel in the gasification. We have to dry the fuel before it enters to the gasification. Gasification itself can be operated with the more wet fuel, but the application in the lime kiln needs that the fuel has to be dried. The gasifier itself, it is kind of circulating bed gasifier that is connected directly to the lime kiln, so that the gas which is flowing from the gasifier to the kiln, that's called the dirty gas. There is a tar and there is also the dust particles that can be burned in the lime kiln. It is unpurified gas, so that the major portion of the wood as is fed to the kiln. Circulating bed material, that's a calcium carbonate, and the kiln power need is controlling the fuel feed to the gasifier itself. We get the primary air back to the gasifier from the kiln cooler, so that the energy efficiency of the gasifier is quite good. We need to have this kind of backfire control system here. It's done either nitrogen or there should be the nitrogen. It's not the nitrogen oxide, it's nitrogen or steam. That prevents the backfire to the fuel feed system. Properties of the product gas is that it's quite hot, so that it's capable to self-ignite. So that normally we operate in the 700 Celsius or 800 Celsius level in the gasifier, so it will ignite when it meets the oxygen. Operating temperatures also above the tar condensing temperature, so that we don't have to worry about the tar condensating in the gas lines. Gasifier temperatures is made by the partial burning, so that the air factor of the gasifier is about 0.3. And product gas content lots of unburnt carbon and the ash from the food, and the heat flow of unburnt carbon is about 20% of the total heat flow. And this will of course burn in the lime kiln, but that's something to be considered if this kind of applications is think in the other processes than the lime kiln. Cold carbon monoxide is heavier than the air, and it won't self-ignite. All these gasifier and the biomass dryer areas are this kind of ATEX classified areas, so that has to be considered when one is building those. This is the energy balance of the gasifier, and that's measured in the Joutseno gasifier guarantee runs, so that when we get the heat flow to the burner, this 36.8 megawatt, this is the amount of the product gas itself. The rest is dust and wood tar, and then of course the heat enthalpy is the some portion of that. So that is the dirty gas, and it has to be taken in the mind when considering this gasifier as in other process applications. But in the kiln it doesn't matter. Kiln can be burning these wood tars and the dust. This is how the burner itself looks like, so that when this biggest channel, that is the product gas, how it's fired to the kiln. The channel is big because the gas volume is high, and because it's a hot gas. It's coming over 700 temperatures, so that's why it's hot. These other portions are much smaller, so that the natural gas you can implement it in a very small burner, and the liquid fuels and the igniters are in the center of the burner itself. And the primary air feed is in the two channels, is entering the two channels. Burner can be operated 100% with the product gas without the support fuel, and fuels can be switched, turned off, turned on quite flexibly, and kiln parameters are how the kiln is operated are exactly same with or without product gas, so that it's operated by the oxygen level in the flue gases and by the residual carbon in the burnt lime. And this is the biomass dryer. How does it look like? So that it's this kind of wire type of dryer. Wood bark needs to be crushed before it's entering to the dryer, and the major portion of the water is pressed away in the wood yard. And the moisture level is after the dryer. It needs to be this low, 5 to 7% level. And there's two major suppliers in the pulp and paper applications. One, Valmet and Andritz, and they are a little bit different in terms of the wire design, but the basic principle is the same, so that it's a belt dryer, and Valmet is circulating this biomass, and Andritz is circulating the exhaust air from the dry end of the dryer. Joutseno process itself, we are operating in the burner power is 48 megawatts, and we have to evaporate water in the bark dryer 12 tons per hour. Our Äänekoski mill is a little bit bigger, so we have the power in the burner. It's 87 megawatts, and we have to evaporate water here over 20 tons per hour, so it's 23.7 tons per hour evaporation rate. Äänekoski we are having birch pine and spruce bark as well as in the Joutseno. Then the experience. This is our CO2 emissions from the lime kilns in the 2020. So Äänekoski, we don't use any fossil energy at all. In Joutseno, we are using some portion. We are using natural gas there. Kemimill is currently operating totally with the heavy fuel oil, and also the Rauma mill. So that as a total, we are producing. Our emissions are there totally in the lime kiln, in the 4 lime kilns. And as a fuel consumption, what does it mean? So that in the Joutseno, we are consuming 260, or in the 2020 we consumed 263 gigawatt hours per year energy in the lime kiln, and over 200 gigawatt hours was coming from the product gas. In Äänekoski, we utilize product gas here in the little bit over 300 or 387 gigawatt hours per year. And in the future, we have the plans so that we replace Kemimill. When the Kemimill is going to be totally modernized, there will be the lime kiln which doesn't use any fossil energy at all, so that the product gas will be the main fuel in the lime kiln. And the Äänekoski mill plan is to use as a sawdust in the primary fuel in the lime kiln in the future. So, did I manage to keep my time, or did I pass it?
Yes, this was the perfect length, and thank you very much for this presentation and insights. Please wait until the end of the meeting to questions and answers. Next, we will have our best case studies presented, and first we go with hydrothermal carbonization of a pulp mill wastewater sludge, and presenter is Peter Axegård, who is Chief Technology Officer at Sea Green Technology.
Okay, thank you. I hope I can get this running. Can you see the slide here?
Yes, we can.
Yes.
Good. Okay, thank you. I will try to keep the time. I will talk about hydrothermal carbonization and treatment of pulp mill sludge, paper mill sludge into a carbon-rich solid product. I will give you a short background and where we stand today as a complement to the results from the project. What we are doing is that we carbonize organic matter in water, like sludge, could be manure or other wet organic waste streams. And this is called pyrolysis, wet pyrolysis, and it's basically the same thing as dry pyrolysis, but we have water. Dry pyrolysis has no water, but in both cases, biomass is treated without oxygen, and carbonization reactions will occur actually. Wet pyrolysis, or commonly called ATC, was first published 1913 by Friedrich Bergius. And the process was idle until the early 20,000 actually, when there were waste restrictions coming up in some countries in Netherlands and Germany mainly, and that was a starting point for doing something with those waste streams. And Sweden has done the same. We started our business about 2015. What we do is that we simply dry sludge and water. That's how it is perceived. Wet problematic sludge converted to a solid product called hydrochar. We call it ATC biocoal, with a much higher dry solid content than sludge. And there are some benefits in doing that. Biosludge in general contains a lot of water. That is one main issue. It is very odorous often, and it contains pathogens at the best. And if we take sludges from municipalities, you have also a lot of other pollutants there. Sludge will always have a very high affinity to metals, and they have a very strong affinity to the solid product we are producing, the hydrochar. So heavy metals have an affinity of around 99% into the solid product. And it has a certain carbon content. The yield of carbon could be 50-60%. Phosphorus has a higher recovery into the solid product, and nitrogen is distributed between the solid water and the hydrochar. This is how sludge looks like in Heinola, in pulp and paper mill, NSSC mill. You see when it's falling down there from a screw. This is rather moist, 15% dry solids, and Stora Enso decided some years ago we cannot deal with this in the old way, like incineration or sending it to landfilling. We need to do something else, and they decided to go for hydrothermal carbonization. That minimized the volume dramatically. This is how it looked like over a year ago. In the background, you see the Heinola mill, the pulp and paper mill, and to the down right corner, you see our plant before the facades were set up. So you see 3 building blocks basically containing our core processes. What more to say here? This is how it looks today. We are trying to have a nice appeal. So this is just a nice image. In the background, you see a big pile of wood chips. We are not processing wood chips at all. Our process, very simplified, is that we take in the water sludge. We heat it, we dilute it, we heat it with internal water. From our process, we heat it with steam, so it reaches 200 degrees. And so we heat this in steps with direct steam and dilution with hot water. The reaction time here is about 1 hour. And here you get the carbonization of the organic substances. So a slurry of hydrochar particles, ATC biocoal particles, is formed and sediments to the bottom. So this slurry is taken out and the water non-press filtering. Here you see the solid product. The liquid phase contains dissolved organics and some nitrogen, and we treat this water with oxidant from air, which the water gets oxidized, or the organic is oxidized, and heat is created, and we recycle steam. So we are completely heat self-sufficient. And it is also possible to produce excess heat at high temperature levels if there is a need for that. Otherwise, we don't do it, and we have more organics in the water. And the water after this treatment is taken back to the wastewater treatment plant. That is the short version. What happens in ATC is simply this, that in the first minute or seconds, I should say, at 200 degrees, there is a rapid loss of gravimetric yield, and this is the ATC chemistry. Most of the molecules in the water is decarboxylated and dehydrated. So, and this means that these molecules are becoming more and more hydrophobic. That's why a solid phase is built up gradually, and sediments. That's why we need up to 60 minutes to get this phase separation, where you have a hydrochar slurry, that is the water, and the liquid phase containing the solid organics is wet oxidation. In wet oxidation, there is a lot of chemistry happening. We do this start at 200 degrees, and then we increase it to 230 by releasing steam. Before wet oxidation, dark is very odorous, contains significant amounts of COD and organic nitrogen. And in the process here in wet oxidation, COD is reduced up to 70%, producing heat. And the nitrogen is converted to ammonium ions that can be used as sort of fertilizer in the pulp mill, paper mill, wastewater treatment plant. And this water from wet oxidation is quite odorous and is very dark, as you can see. And the wet oxidation removes the color and it eliminates the odor, because the ATC water is concentrated odor from sludge, basically. So yeah, we treat a lot of different waste sludges, food waste, food digestate, biogas digestate, sewage sludge, manure is possible to deal with, and also other sort of sediments that can be found all over in Sweden and other countries. We're working on that as well. So the process takes 1 hour, and we don't add any heat. We increase the dry solid content between 50 to 70%. On a sewage sludge, 60-65 is normal. So it depends on the type of sludge we are treating. There is a large water removal. That is a main driver, of course. And the solid product has a lower heating value, ranging between 4 to 11 gigajoules per ton. It depends on the ash content and achieved dry solid level. And it's sterilized and is odorless, in contrast to sludge. This are some slides from our plant in Heinola. This is a sludge, I showed you that before. This is the hydrochar after the press filter when it's falling down in the transport container. And here is a more close up on the hydrochar. You see 2 centimeters basically in thickness. And Heinola currently is used as a biofuel in the bubbling fluid, the boiler, together with peat. Here you see the ATC reactor, here is some piping and heat exchangers, and here is the press filter. And the whole process is completely closed. So there are only water leaving the system, hydrochar leaving the system, and vent gases that are treated. So it's the closed process. Applications, biofuel, of course, is an interesting opportunity. In contrast to sludge, that has a negative heat value. And this is, I would say, not recommended because the customer decides, but It makes sense in some cases where the pollutants involved, then incineration in a classified boiler is the way to deal with it most likely. But we also look into soil applications, and if you have a relatively clean sludge, this is an interesting opportunity. And often in Sweden, I guess Finland, peat is used as a sort of soil additive together with other feedstocks. So hydrochar could fit nicely into peat mixtures. And this hydrochar contains nutrients, and we have some water retention capacity and things like that. It is relatively stable in soil, so there are some benefits environmentally. So I will show you some slides here. Heavy metals in the hydrochar, you see for different feedstocks range. This is the pulp mill case, the gray one. This is the limit values for soil applications in Sweden. And all feedstocks are below the threshold level except manure. And assume that they were using some cadmium containing nutrient on soil on that land. Mercury is well below, nickel is well below, and lead is also well below. So soil applications from this point of view could be possible. Looking on the nutrient side, these hydrochar, they have a relatively high amount of organic carbon in percentage of dry solids. Carbon-nitrogen ratio is within the limits of humus in soil. And here is the amounts of different nutrients for different feedstocks. And the left number is the total amount in kilos per ton, and the right number is what can be leached with a method simulating what roots are doing. It's a lactate leaching method. And the pulp and paper mill biosludge has a high plant availability for these nutrients, except for phosphorus. While food digestate in general has a very good capacity, and sewage sludge, it has the nutrients are quite unavailable. These are grab samples, but you can see that the chemistry differs a lot, and a lot is to do with the chemicals used for precipitation of stuff in the wastewater treatment plant. Some sort of plant trials. Peat is not a good source as such because it's not rich in nutrients and rather acidic. The sludge from Heinola worked quite nicely. Sewage sludge, and in this case, looks quite fine, and food digestate. And this is this is pak choi, and this is actually another plant, but I will correct that. So soil application we think can be interesting if you combine them with the carbon sequestering effect. Just basically the last final slide, we have a pilot plant for hydrothermal carbonization. It's on its way down to Stockholm here, and here it is set up on site at Roslagsvatten. It's a water utility in north of Stockholm where we're doing trials. So to sum up, we believe that ATC and wet oxidation is a new, but we think it's a powerful combination. And inorganic sludge can be converted to odor-free, sterile ATC biocool / hydrochar. Applications, biofuel, soil improvement, and potentially even as activated carbon. Work is going on in that area at the University of Umeå. So that sums up where we stand now. I hope you understand a little bit of what we do. So I thank you for attention, and if you need to know more, you can contact me here or in the question session after the presentations. So thank you.
Yeah, thank you very much, Peter. Nice presentation and nice pictures of a bioenergy retrofit as well. Next, we have the other case study of BioFit presented by Tobias Geplinger from Austersel Hallein. It's about fermentation of liquor at Austersel Hallein pulp mill for advanced bioethanol production.
Many thanks. Can you see my slides already?
Not yet, it's black.
Okay, I'll try again. Now?
Yes, now we can see it.
Yes, but it's not in presenters mode.
Yeah, I will start, hopefully. Now it should be in presenting mode,
Yes,
correct?
perfect.
Perfect. I will try to get the pointer. Yeah, here it is. Yeah, many thanks for the introduction. It's a big pleasure to give you an overview, or a very brief overview on one of our major projects within the last 2 or 3 years, which is the production of advanced bioethanol in our pulp mill. I want to start with a brief introduction, so who we are, and then how this bioethanol project fits into our portfolio of products, so to say. So basically, where are we located? We are in Austria, as you know, and we are in Hallein, which is quite close to Salzburg. And I also want to give you a nice top view of our mill. So as you can see here, this is the whole mill area here, quite close to the river Salzach. And here on the right side, you already see the starting point for all our products, which are the wood chips, so to say. So out of the wood chips, we make everything: our pulp, our bioethanol, our biogas. So this is the big starting point. And in addition, as you can see, it's a very nice place to work. It's a beautiful scenery. So after COVID, I would be more than happy to welcome you in our mill to show you the bioethanol production. So and after that visit, you then can enjoy the nice area in Salzburg. So I want to give you a brief history, because I think it's important to understand why this bioethanol production was so important to us. So basically, the pulp mill in Hallein is one of the oldest, or the oldest industrial company at the same place in Austria. So basically, we are operating at the same place since 1890. And over the years, we had different owners, and of course, there have been different retrofits. But I want to only highlight one major year, and this was for sure 2009. In 2009, we stopped our paper production. Of course, this was a big cut. And at that point, we were starting to think what could be a possible economical scenario in the future, which kind of products, which kind of strategy. And this is for sure also the starting point for our focus on bioenergy in general, because we decided at that point to switch our production from paper pulp to viscose pulp, and in addition to bioenergy applications. And this was during the last years since 2009. So basically, we invested a lot into our biogas production, and after the biogas production, we started to invest or to build up our bioethanol production. And just some numbers about Austrosen in general. So as I've said, our main product is still dissolving wood pulp, so high specialty wood pulp with a very high purity. At the moment, we are producing around 120 to 140,000 tons of pulp. We are about nearly 300 people in the mill. As I said, we also produce green electricity based on biogas. So we provide this electricity to the national grid. We also have, of course, some excess heat, which we also provide. So in total, for example, we can provide at the moment green electricity for 25,000 households, and district heating for around 30,000 households. And of course, since about 1 year now, we are producing bioethanol at the moment with a capacity of 20 to 25 million liters per year. But of course, with the goal to entirely utilize the capacity of a bioethanol plant, which I will show in the following slides. The capacity what we have is about 35 million liters. So there's still a way to go, so to say. I want to just show you how the bioethanol production is embedded in basically this in the dissolving wood pulp production. I'm pretty sure you're all familiar with this topic, so I will be very brief on that. So basically, the whole idea of dissolving wood pulp production is that we produce high quality pulp, which is then used for the production of fibers, and then at the end to textiles. I just want to highlight here one important point is that in terms of a cascaded utilization of the great resource, the renewable resource wood, is that we are using waste wood. So basically, wood which is not used in, for example, in engineering anymore. This is the wood what we are using to produce our pulp. And then this pulp we sell, and out of this pulp, then the textiles are made. And I'm pretty sure all of you know that during the pulping or during the production of pulp out of wood, the main component what you're utilizing is the cellulose. But the cellulose is only around 40% of the total composition. So it is very important for an efficient process to also make use of the rest of the wood components, which are the hemicellulose and the lignin. And during this pulping process, what you get is during the pulping and during the cleaning is you remove the other components. For example, the cooking liquid is composed of lignin and sugars. And the great thing about this brown liquor is that the sugars are already in this brown liquor as monomers. So you can directly make use of these released sugars, for example, which I will show you in the next slides, for the fermentation and to produce bioethanol. But of course, you also remove filtrates and rejects during the cleaning of the pulp, so to say, and it is also important to make use of them. And just one example is how we make use of them, of these filtrates, and then I will come to the bioethanol. Out of these filtrates, what we are doing is a biogas production. So this is organic material, and we feed this organic material into 4 biogas reactors, and then we are producing biogas out of it at the moment with a capacity of around 2,000 cubic meters per hour. And this biogas we then feed into quite a large biogas motor with about 5,000 horsepower. And out of that, we are producing then quite a substantial amount of electricity. But of course, we also have a biomass CHP, where we also put in internal residues, what we get out of our pulping process. And out of that, again, we are producing electricity on the one hand and heat, which we on the one hand put into the national grid, but also, of course, for our internal needs, we are using this heat in the form, for example, to run the drying machines for the pulp production, so to say. But of course, the focus today should be a bit more on the bioethanol production. And so I will give you a brief overview over the project. So basically, bioethanol production in Hallein is not new. There was already a bioethanol production from brown liquor during the years from 1941 to 1988. You can see here on the top right and quite an interesting image where you see this was basically made of, during the first delivery of bioethanol from our mill, and this was, as I've said, in 1941. So basically, at that time, we had a capacity, a very low capacity, around 6,000 liters per day. But because there was over 4 decades of bioethanol production at our mill, there's a very long-standing experience or process experience with brown liquor and biotechnology in general. And this is very important because actually brown liquor is a quite challenging medium for the bioethanol production. So basically, based on this long-standing experience, basically there was quite a calculated technological risk for a new project to build up a new bioethanol production for second-generation bioethanol. Then during the years 2007 to 2009, there was already quite a comprehensive pre-project and feasibility study. And for example, the economic feasibility was determined. There was also quite some research and development going on. But as I've mentioned before, in 2009, our paper mill was shut down. So it was, in terms of economical situation, quite a challenging situation. And so it hindered to realize this project. And then, of course, in 2011 was then made, as I also mentioned before, the switch to producing dissolving wood pulp. And that's a very important point, because when you're producing dissolving wood pulp instead of paper pulp, so to say, then of course you're producing a pulp with a very high purity. And the high purity means is that you remove more of the sugars or more of the hemicelluloses. And this of course means more sugars in your medium or in your liquor means that you can reach ethanol yields which are significantly higher compared to a system where you're using the liquor from paper production, so to say. So basically these are the main points which are then, so to say, the starting point for our bioethanol project. How did we integrate the whole bioethanol production in the pulp mill? As you know, there's quite a already, so basically what was the challenging thing or the important thing is how can we implement this new process into the existing pulp mill production. And so to say, I've highlighted here in orange the situation before our bioethanol production. I just want to briefly go through the process. So basically, you're cooking the wood chips with your liquor, and then you get the liquor out of it, so to say. And this liquor, typically, you run through an evaporation plant with different steps, and then in order to concentrate this liquor, and then you put this concentrated brown liquor into a plant where you burn it, and then there are two main points for that. On the one hand, in this plant, you can recover chemicals, which is then going back to the pulping process. But of course, what you also do is you generate energy, which is also important for our mill. But of course, there's a surplus of the brown liquor, so you cannot burn everything. And this brown liquor we sell then to other customers. So this was the situation before the bioethanol project. And during the bioethanol project, we had to implement the bioethanol production in this existing scheme. So what were we doing is that we make a side stream, so in the middle of the evaporation unit, so to have something like a pre-concentrated brown liquor, as it is mentioned here. And this pre-concentrated brown liquor, which consists already, or which has already in it the sugars, we put this into a fermentation facility. And in this fermentation facility, we are doing a continuous fermentation, which is actually quite new, so to say, on that scale, and which is also different to classical batch fermentation facilities. And then we ferment the slurry, and this fermented slurry, basically, which contains then the ethanol, we run into a distillation plant, and basically we remove then the ethanol. And the ethanol-free mesh, basically, we then put again into our evaporation plant, which goes on with the evaporation and goes again in the already existing scheme what we had before. And of course, the removed ethanol with very high purity, it's around 99.9%. As I've said, at the moment, we have around 20 million liters per year. We are then pump into a filling station, we fill the trains, and the trains are then going directly to our customer, which is at the moment OMW. So one picture of our bioethanol facility you can see here. So this is just the planning. As I've said, basically there are two main parts. Here you see this fermentation tanks. Here we have 4 of these. Here is the continuous fermentation is going on, and then the fermented slurry goes into the distillation plant with the big distillation column. Yeah, and here is an image you have seen already before. It's a bit difficult to, well, you see not too much, but actually what you can see here is the building with our fermentation tanks. And here in the back, you can see the end of the very large distillation column. And here you can see the railways and the filling station. And of course, this is also very important that you have a railway connection where in order to transport then the bioethanol to the customers. What else? I also want to briefly highlight that for this project, one of the main things what was very important in order to have a successful project is research and innovation. So basically what we do in-house, so basically all the development in terms of fermentation, in terms of testing yeast, to developing yeast, we did in-house. So this is, so to say, expertise what we have in our research department. This is, of course, then connected with all the according analytics in terms of HPLC, sugar analysis, and things like that. I think this is very important because, as I've said before, this liquor is quite challenging in terms of inhibitors and things like that. And you need this in-house expertise to, well, to have solutions when there are any kind of problems during the production. So basically what we all have is not only lab scale, what we are doing, or lab scale experience. So we have a fully functional pilot unit, which is basically a 100% replica of our process in the industrial plant. This means here, as you can see here in the back here are the fermentation tanks. So within a capacity of a couple of 100 liters. So basically if there, we can basically run and test systems one-to-one which are one-to-one comparable to the system what we have in the industrial plant. I think these are important factors to be successful for a project like that. In summary, for this bioethanol project is that we successfully implemented this bioethanol production in the brown liquor cycle, as I've described before. The whole project had about an investment of 42 million euros. Here you can already see a So this is the visualization of an issue what we still have, of course, that typically in fermentation, what we are using at the moment are the C6 sugars. And of course, the C5 sugars at the moment are not utilized. So it would be, of course, a significant potential to if we would be able to use also the C5 sugars in terms of the ethanol yield. Of course, what is also important to mention for an investment or a project like that, it is highly important that you have some kind of long-term offtake agreement, and this is what we had with OMW, which of course then secured the investment. I think it was also mentioned before that the 35 million liters would more or less represent 1% of Austria's gasoline demand at the moment, and of course all this emphasis on for the bioethanol production in our company is of course embedded in the legal basis of the European Union directive, where you have to substitute fossil transportation fuels by advanced biofuels, where you have these values as you can see them here. I think this is already it from my side. If there are any questions, I would be more than happy then to answer them after all the presentations. Also would be happy if there's any kind of input. I would be also more than happy to have that. And this is our motto, Austrocell is fighting the climate change, don't talk, just do it. And I think with this project, this is exactly a support for this statement. And many thanks for having the opportunity to present this project here. And yeah, thank you.
Thank you very much, Tobias. This is a good motto and a nice plan you have there. I will present the last presentation myself. It's concluding the results that we have in BioFit project for the sector. Let me know if you can see my slides now.
Yes, we can see.
Yes.
Thanks. So to conclude, as you have heard today, Bioenergy Retrofit lead pulp and paper industry towards new possibilities. First, I want to show you some statistics from CEPI to showcase the size of the sector that we have in hands. We have almost 900 mills in Europe, producing annually 36 million tons of pulp and 85 million tons of paper and board in Europe. The number of mills has steadily decreased since 90s, while at least for the last decades, the pulp production has stayed relatively stable. And as you heard already, sector is revising their business models, seeking for new high-value products and widening their product portfolios. And here, bioenergy retrofits can also help. Next slide. Okay, then about the energy consumption and fuel consumption in the sector. The sector already covers 60% of their total fuel consumption and more than 50% of their total primary energy consumption with biomass. The primary energy consumption in sector has decreased due to energy efficiency measures during the years, and the share of biomass used for energy has also increased. However, still there is almost 40% of the total fuel consumption covered by fossil fuels in the sector. So there is room for bioenergy retrofits. Here I want to show you the map that we have made, and it can be found from BioFit web pages. We have mapped the current known retrofits for pulp and paper sector, and here you can also see what kind of side streams these retrofits use. There are a lot of them, also a lot of different type of technologies. I have the links to our case studies and best cases here as well, and also all sort of different kind of products. This means that although we have a lot of dots on the map, most of them represent different type of technologies and different kind of retrofits, which makes it hard to have an experience to retrofit more. Then drivers, Christian already talked a bit of this. So we have digitalization, which decreases print paper consumption globally. And that means that we need to find new products for the sector. Then we have climate change mitigation. We need new renewable energy sources, fuel sources, and product sources. And also, as Tobias highlighted in the last slides, we have targets, especially for advanced biofuels, and actually most of the side streams listed in the previous slides are listed there in RED II directive. I think it's Annex 9. The side streams that can be used for advanced biofuel production and is count to this target. So there is a good opportunity. Then we have circular economy initiatives and sustainability issues in the sector. So we need to use the raw material more efficiently, and this is something that in which bioenergy retrofits are also useful, and they can increase the energy and material efficiency of the plants, especially if there is excess energy at the plant. What is needed then to do the retrofits? As Christian told, they are not directly replicatable from mill to another, but it depends on the pulping technology whether we can actually use a certain retrofit. Also, it depends on the local conditions at the mill, what is there in the place, and if there is markets for the end products at place. Also, the volume of side streams restricts. If there is not enough side streams, then we don't have a lot of final product. So the feasibility must be assessed case by case. However, we have found cases in which the retrofitting leads actually the further retrofitting. For instance, Norske Skog's mills from first biogas production plant, they extended retrofitting to other mills of there. Also, we heard that the gasification that started in Joutseno has been extended to new mill in Äänekoski and is planned to Kemi mill that is going to be built. When you think producing new products at the mill, you of course need to think the whole value chain from the production to customers. And this is very essential. Some of the retrofitting products also need further refining before entering the market. So you might need connections there as well. Here I have a picture of Domsjö Fabrikers in Sweden that is producing bioethanol and selling it to SICAP for further refining. Some more challenges, as Christian told, there are still mills, especially in southern and central Europe, that are not connected to pulp, paper mills that are not connected to pulp mills, and they have problems in accessing the feedstock, biomass feedstock. So retrofitting there is difficult. But some of these technologies might be possible to use there. In the next questions and answers slot, I would like to ask, for instance, from Peter, whether HTC technology would be suitable also for these mills. But let's do that then. Also, as Christian said, these technologies are in different TRL level, so it's not easy to assess whether the technologies are actually feasible. Also, rapidly changing policy and market conditions affect. We have feedstock that can be used to other things besides energy. So so there can be changes, and then we also have a wide variety of products with different, which market price might change. And when you're planning a retrofit, this is a challenging case to think whether there will be markets for the entire lifetime of the plant. Then sector is also affected by international competition. To conclude, some recommendations for the sector. We recommend that the research and development funding as well as investment support is targeted to technologies that allow efficient side stream utilization and increase overall efficiency of the plants. Also, we need some long-term political support and consistency in development of regulatory framework. This enables these investments that require some high upfront investment. Then also we have these mills in Central and Southern Europe that are using natural gas as their feedstock. Their research and funding allocated for broadening the feedstock base could be helpful. And also this problem, we would like to give some awareness towards this problem. Then to tackle the international competition, the European Green Deal has proposed carbon border adjust mechanism which is of importance for the sector. These were my conclusions. Lastly, I was asked to present also the digital support tools that we have made in the project. These are made based on 5 case studies in the project. So for 5 different retrofitting technologies, one for each sector. We also have pulp and paper digital tool there, which is based on the case study of HTC that was presented here earlier. These are easy to use. You can evaluate the benefits of bioenergy retrofitting, roughly assess the techno-economics with parameters that you want to set there. Now I change the view to show you where you can find this tool and a little bit show you how it works. So wait a sec. Okay, now can you see BioFit web pages there on your screen?
Yes.
Okay, yes, here on left-hand side, the second, we have a BioFit digital support tool. And if you click here, you go to the pages where all of the tools are listed. We have one for district heat production, pulp production, fossil refinery sector, 1G biofuels, and for fossil power sector. And there is a short explanation of all of these. Then if you click here below the certain retrofit, this is the pulp and paper sector retrofit, you can actually get to the tool. Here we have a short introduction, first leaflet, the short introduction to the tool. Then we have a block diagram showing the reference case, what was there at the plant before retrofitting, and then the retrofit case. And here you can modify some assumptions already. For instance, in this case, you can determine the amount of sludge you have. Then with this assumption and some other assumptions that you give, you can calculate the net present value of your investment. Here and you can give costs, how you think the electricity price is, or for instance the product price. If you here increase the product price, you can see that the retrofit becomes more feasible. Then we have the cash flow with same assumptions here. You also, if you change the parameters, you can see how it affects to internal rate of return. For instance, if the electricity price is getting down, I think that might not be the case, but anyhow. And lastly, you can evaluate the emissions from reference case to retrofit case. What happens with certain assumptions? Here you have the description of the boundaries for the calculation. So please go there and test the tools freely. Okay, that was the end of my presentation, and now we can go to the questions. We have already gotten some into the chat already. If I can ask all the presenters to show, yes, all are there, and we can start. Is there any questions, or do I go to the questions from the chat? Jan from Laborelec.
Yes, thank you. I have a question for Peter from Seagreen. So because we are also very interested in HTC, yeah. So Laborelec is a research center. We also looking at HTC. And when I saw your diagram in your presentation regarding the Finland case, I saw that the water after the wet oxidation was sent back to the wastewater treatment plant. Nevertheless, you mentioned that due to the wet oxidation, the COD was reduced with 60 or 70%. Does it mean that even the water after the wet oxidation is not yet clean enough, for example, to use for irrigation? And then what brings me to the next question, that is, let's say that the water, yeah, just so after the HTC, is that today the main challenge in HTC to make the project, let's say, profitable?
Well, actually, very good questions. First, with irrigation, it depends on the origin of the sludge, I would say. It depends on the amount of heavy metals, which normally is quite low in pulp mill sludge. Could be elevated in cadmium in some cases. And there are very, very little of other contaminants like PIH, PFAS, and PCBs, dioxins, pharmaceutical residues that you have in sewage sludge. So sewage sludge, I think that is not a good opportunity for irrigation. But we actually have a case in Sweden where we are considering, together with the producer of soil products, to use our processed water for irrigation. That discussion was sort of taken off yesterday, and it makes a lot of sense, because if you are allowed to apply sludge on farmland, if you fulfill certain criteria in terms of contamination, and it regards especially heavy metals, we know that the amount of heavy metals for a given amount of sludge is just 1% than what you have in the sludge. So if sludge usage on land is okay from a metal point of view, the processed water is much, much leaner in heavy metals. Therefore, it should be, in principle, okay. So we're looking into this heavily now. But I would say it depends on the feedstock. You ask if the water is the main challenge. It depends on the case, I would say. In Heinola, it's not a problem because they can utilize the nitrogen and replace commercial ammonium nutrient like urea. While in a sewage plant where they treat sewage water, they work heavily on removing nitrogen from the process streams, and adding back nitrogen would sort of make this more complicated. So nitrogen, I think, is the main issue if you talk about sewage treatment plants, while in pulp and paper mills, nitrogen is not an issue. So it depends on the case. I hope I clarified a little bit.
Yes, thank you.
Tobias, you had a question?
Yes, I would also have a question to Peter. So basically, what we do, or what we have, is of course we also have sludge in our we get sludge in our wastewater treatment. And typically, what we do, we then do a simple dewatering and then put the sludge into our CHP plant. So my question is, would it make sense to put your process in between, or is this a possibility?
It is a possibility.
Or does it make sense? Let's put it like that.
Yeah, it depends. What is the limitation? If you have a limitation in incineration capacity due to the water vapor, that could be an issue. Mm-hmm. And in that case, it can make sense. But it depends on the situation.
Okay. Thanks.
Okay. Then we have a question in chat for Christian from Luke. With declining paper markets, do you think that pulp mills could be converted to biorefineries with higher focus on bioproducts or biofuels and less on pulp?
Yes, thank you. Good question. I also already answered in a long way that in the chat, but maybe I can comment. So I think that so far I have not seen so much interest to produce something else than pulp. Maybe that is because of the economics. I think what is typically considered, even though the paper decline is decreasing, so typically the mills look at ways to, for example, make the textile pulp, and in Finland we have several different companies also with new technology who are developing this. So I think there is more activities than, let's say, to make something from lignin, maybe not so much biofuel, but other bioproduct and so on. And of course, like quite a long time ago, I remember I was in the course in Aalto University, and there I heard some discussion that there had actually been some pulp mills that were planned to be closed, but they were converted into bioethanol facilities. So basically, they were producing bioethanol from the pulp, and in some calculation that seemed even quite promising. But of course, that is only then like interesting in such a case that you don't have like demand, or for the price for this pulp is very low and so on.
Could I add a comment here, maybe? Is Peter?
Yes, sir.
Yeah, just to add, what I could say is that if a pulp mill would turn into other products, it needs, for a given configuration, take a new crop pulp mill, for instance, you need to have revenue corresponding to what you get from cellulose.
Yeah.
And if you make fuels, you get maybe 10% of the revenues for the same capital need and same OPEX. So that's why it doesn't make sense unless you make cheap bioproducts from waste streams. So I think this industry needs to valorize the main components in the wood, lignin and cellulose. And what I've noticed is that there is enormous effort in different kinds of nanocellulose now. It's a big focus on that in many companies. We don't see much officially, but there is a lot of things happening in the nanocellulose, microfibril cellulose area. And it relates to packaging, it relates to new products, and renewable plastics and stuff like that. And as I think this would be much bigger business in a couple of years than the lignin business, because of the value per ton of product and the performance increase.
Yeah, it's very good. Can I fastly add one point also? So actually also, I didn't mention it earlier, but also actually at Ultan, and we have been involved in some activities with hemicellulose, let's say from side stream from sawmills. And if there will be also a way to get good hemicellulose streams, in polymeric hemicellulose, they might also have very interesting application. For example, thickeners of paints, and they are also quite valuable.
Yeah.
Thanks.
Yes.
Then we have question for the gasification. Manolis asks whether you can estimate the capex cost of the gasifier with or without the belt dryer? Mike is still muted.
That's better this way. I can give this kind of rough idea that what is the capex level, and we are talking about 30 million euros in terms of the investments, and about half of the investments is going to the belt dryer.
I myself have another question related to feedstock for the gasifier. What was done with bark before this retrofit? And is it do we have enough feedstock for the gasifier?
Yes. Before in the Joutseno mill, because in the Joutseno mill we don't have the bark boiler. We don't have the only boiler in the Joutseno pulp mill is the recovery boiler. So the extra bark was sold as a fuel to the neighboring cities, like a city of Lappeenranta as the fuel in their boiler, and the normal size of the pulp mill can feed from the debarking plant if the purchased wood is the round wood, so that it needs to be barked. About half of the bark is needed to feed the gasifier and feed the lime kiln, and half can be still sold as a fuel outside of the mill.
Still another question from my side. How has the technology worked? Has there been problems or shutdowns, or is it running smoothly?
The gasifier itself that has been running pretty smoothly because we have now the experience about the 10 years of Joutseno mill. But in the startup, there has been the starting years, there was some problems in the wire, in the belt dryer. We estimated the capacity of the dryer a little bit too small, so the capacity has to be increased, and the fires have been also the cause in the dryer. So it is this kind of ATEX classified area which which has to be taken very seriously in terms of the fire protection.
Thanks. Then we have a question in the chat again related to HTC process. Raquel Iglesias from CERMAT is asking, is it possible to use this HTC biocoal as CO2 absorption carbonaceous material?
I heard this question before. Maybe, I'm not sure. This material has a quite low porosity. I think that can be a challenge. It has a very low surface area in terms of BET analysis. So I doubt that.
Thanks. I had a question in my presentation already to Peter, whether this technology could be suitable also for sole paper mills that are not connected to pulp mills. Do you think there would be enough feedstock at those mills to use for this technology?
Well, ideally, we normally say that we can treat about 5,000 tons of dry solids per year. And if you turn down the utilization to 80%, 4,000 tons of dry solids per year. So that would be my starting point. Yes, it can be, and actually we have been working with chemical sludge, tertiary sludge, and even that can be actually made a lot drier actually after our treatment. That is a benefit. And that is a complicated sludge because there is no really use for that except landfilling. So that can make sense. And we took a case where the ash content was 60%, and we got a very high solid content of the hydrochar. But we need a couple of thousand tons of dry solids per year to make it sensible economically.
Thanks. We have a question in chat from Jan again.
I'm muted, thanks. A question for Pertti regarding the belt dryer. Because I missed a part of the presentation, my apologies. I suppose it is air dried, hot air, I suppose. And do you have an idea what the consumption is in kilowatt hours per kilogram water?
Yes, it is right with the hot air. So we are utilizing the secondary heat as a heat source from the hot water or wastewaters, and the rest is coming from the back pressure steam. So that the heat air needs to be around the 90 Celsius when it's going to the wire. So the heat source must be, of course, higher than the 90 Celsius. This can be maintained. I don't remember my heart the efficiency of the evaporation, so that how much secondary heat does it consume, but definitely it's more than the evaporated.
Yeah, indeed.
Evaporated water latent heat is that. Sorry, I don't remember that because we are using the secondary heat there.
Okay, thank you.
Thanks. I have a question to Christian. In your presentation, you showed that there are a lot of retrofits using black liquor from pulp mills. Can you do several retrofits at the same time, or is there different parts in the black liquor that can be used at the same time?
Yes. Okay, good question. I think that it would maybe make sense to do one of them, for example, or otherwise it becomes quite costly. For example, I would do either this hydrothermal liquefaction or then black liquor gasification. But of course, that if you have a lignin extraction, you could do something with the lignin, and of course, that would be possible then to combine with some other type, then using the rest for something else, for example, hydrothermal liquefaction or gasification or these kind of things. Yes. Yeah. And Heidi, by the way, did you see Tobias? I think he has his hand up. If you want to ask some question.
No, sorry. Sorry, maybe.
Yeah.
Okay, it was earlier.
Yeah.
So.
Yes, sorry. I thought it was earlier already.
Now it should be fine again.
Okay, then do we have more questions from the audience to presenters? In chat, Luke is asking, apart from processing residues like bark, are there also primary harvesting residues from forests used for energy in pulp and paper mills? Christian, do you have an answer to that?
Sorry, can you tell again? I missed part of the question, so can you say repeat it?
Apart from processing residues like bark, are there also primary harvesting residues from the forest used for energy in pulp and paper mills?
Yes, good question. I think it's not actually used in this pulp and paper industry. What I showed this first slide where there is the collections chain. So, for example, this like harvesting residues that you get in the collection. So I think what if they are utilized somehow, so they are typically then transported to separate, like for example, CHP plant or this kind of facility.
Thanks. Any more questions from the chat? From the audience? If not, then I can conclude this session and thank all the presenters and all the questions. Also, we seem to have very many options in pulping industry for bioenergy retrofitting, and I think this is very good for the future of the sector. Next, in BioFit final conference, we will have a session for biofuels, and if I'm not mistaken, it will start 11:15. Am I right, Doris?
Yes, that's right.
Okay,
So
so
11:15.
Yeah. So then we have a short break, and those who are interested in the next session can come and listen to that as well. I hope that presenters can send the slides and we can upload them into the BioFit web pages. And if more questions come up, you can send them directly to the presenters. Thank you.
Thank you.
Thank you.
Thank you.
Thank you,
Thank you,
Heidi.
everyone.
And not to lose much time, I think we will just start. So welcome everybody to this final session of today in the BioFit final conference. We are in the industry session about first generation biofuels. I will start to share my screen now. So you should be able to see it. Is that true?
Yes.
Yes.
All right. So then, my name is Arne Gröngröft. I work for DBFZ, and I will chair today this session together with Raquel Iglesias from CIEMAT. So we have divided the session between us a little bit. As you might have heard in the session before, if you were already there in the morning, this session is being recorded. So if you don't want to be recorded, please, yes, ask your questions in the chat or switch off your camera, just so that you know. Okay, then I will now start into the session with a short presentation of the status quo of the biofuels sector, or some background to the biofuels sector, and some BioFit activities that we did for the biofuels sector, just as a starting point for this session. So, as to start with the overview of the first generation biofuels, the main source for greenhouse gas mitigation in the transport sector are still first generation biofuels. These are being used as blending components into diesel or gasoline fuels, and that is already the big, or the one subdivision that you can make in the biofuel sector between those two applications. So are you going for diesel or gasoline? There are also still some other sectors like aviation and marine fuels, but these are not very much developed so far. So when we look into the production of biofuels over the last years, we see here on the right-hand side these bar graphs of the European biofuel production. In the upper blue box, you find the biofuels for the diesel sector. In the bottom part, you find the biofuels for the gasoline sector, and the composition of the feedstock, or the feedstocks that are being used for these for the production of these fuels. So overall, you can see that there has been a quite stable production over the last years, after a rather steep increase in production from 2006 till 2000, let's say 16 for biodiesel, and 2006 until 2012 for bioethanol. But since then, the production has been rather stable. In the
biodiesel sector, there has been some additional production of biofuels from used cooking oils and yes, until 2016, but also that has been stable, rather stable since then. But what you can also see from these graphs is that the main inputs currently are still agricultural crops with still rather small shares of residues, such as used cooking oil and animal fats for biodiesel and hydrotreated vegetable oils, and a very, very small share still of cellulosic biomass for bioethanol. Although here it has to be said that the increase of the production is ongoing. So there are plants for lignocellulosic ethanol being built by Clariant at the moment in Europe, for example, and we have just also heard of an example of additional production from Ostrocell Hellein, for example, and there are some more activities. So this is just an overview of the situation of the production. So what is being the efforts are there to produce more waste-based biofuels, but they are not much to see in the market so far. A different view on the biofuel sector is the view on the impact they have. So this is just a graph showing the improvement in greenhouse gas emission savings from first generation biofuels. So here it's just for the German market, but it is a timeline of the greenhouse gas emission savings for different types of biofuels. And you can see that the savings compared to fossil fuels have increased since 2011 until 2019 quite significantly, and some of these increased or these better greenhouse gas emission savings from the biofuels, of course, result in retrofits in the plants. Some effects are also in the organizational structure of the biomass feed chain, or so there are different factors, but you can see that they are quite efficient already. Now, if you take a look at the overall transport sector and the goals there, and you can see that there's quite a big gap between the trends and the targets in the sector. So in this graph, we have the final energy consumption of the transport sector. This is for Germany only, but I think it is comparable to other nations also, and also on a European level. So on the left-hand side of this timeline, you see the history of the final energy consumption in the transport sector, with road transport, aviation and marine sector on top of that. And on the right-hand side, you see in red dots the target values, and you can also see some scenarios how to get there. And you see that the trend is not really going downwards, whereas the targets are quite difficult to meet, probably. So this is the final energy consumption, and even more drastically, you see this this gap when you look at the greenhouse gas emissions. So it's not the energy anymore, but the emissions. And here you also see that we don't really have any, or the trend of the emission reduction in the transport sector does not really show any movement towards the target values that are set up. For example, greenhouse gas emissions until 2030 of -42% and 2050 of -95%. This is for Germany. Yes, so there is quite a big need to still do something in the transport sector, and retrofitting might be an option here. Something quite special about the biofuel sector is that it is already a quite highly regulated sector. There are many policy parts coming from the European side being transposed into legislation on member states level, such as targets and quotas for some biofuels, like advanced biofuels. We have a target to reach 0.2% in this year, then 1% in 2025, going up to 3.5% in 2030, according to RED2. Then we also have some other targets in the aviation sector. For example, ICAO has the target of reaching 50% greenhouse gas emission reduction until 2050. But we also have caps for conventional biofuels, so not targets where we want to go, that we want to reach, but caps of how many biofuels should be produced. And we have a quite elaborated system of sustainability criteria for biofuel production. So there it is a highly regulated sector. Yes. So all of these things are to be kept in mind when we looked for drivers for retrofitting of biofuels. So we sat together in the project and came up with a list of drivers that are here not in a very specific order, but some drivers for doing retrofits in the biofuel sector are feedstock change from agricultural feedstocks to residues. This is because of benefits on the market, for example, double counting of the greenhouse gas emissions for those feedstocks, just lowering the greenhouse gas emissions in the production chain as a market benefit. Then the production of biofuels for different applications, for example, marine or aviation sector, whereas aviation sector is probably even more important. Then not only biofuels are being produced in the facilities, but also byproducts. And if these are being upgraded to byproducts with a higher value, then you can generate additional income. Another topic was found to be the flexibilization of the feedstock that can be used, so that you can react on market developments on the feedstock side. Also, something that was mentioned was the quality improvement of biofuels, so that you can also there have additional income because of better qualities. This is especially for the biodiesel sector of interest. Then something that might be interesting even more is exploring synergies with renewable electricity generation and CO2 utilization, which might also be a driver for retrofitting of biofuel plants. So what have we done in the BioFit project? It was already presented in the morning. We have compiled a map of the facilities, of retrofitted facilities and fact sheets, and we have written a handbook on technical options for retrofitting, where we also looked into technical options. We will hear more about those later on by my colleague Stephanie Hauschild. We have held industry fora with experts from the biofuel industry. We started with a meeting in Leipzig on retrofitting measures with a special focus on biodiesel plants. We have had a very nice and large meeting in Madrid about retrofitting the first generation biofuels, which was more focused on bioethanol. And then we had several in the later part of the project several online activities. Unfortunately, there were no more face-to-face meetings to this topic, which is a pity, but yes. And we also held some surveys on drivers and barriers and the public acceptance. And from all of these activities, we came up with policy recommendations, which will be presented tomorrow at the policy breakfast, which you're all invited to, and also some sectoral recommendation paper for the biofuel sector, which so many of these informations can be found on the website. And some the next important point that we did was we conducted 2 case studies within the project. One for the company Vertex Bioenergy on the retrofit of the first generation ethanol production facility of Biocarburantes de Castilla y León to produce advanced ethanol, and one for Swedish Biofuels about the benefits and challenges and opportunities of integrating alcohol to jet technology into an existing 1G bioethanol plant. Yes, and these case studies were conducted together with the partners of the BioFit Consortium. But we will hear more about the details of those in a couple of minutes. Yes, so this was my brief introduction into the session, and we will now continue to hear some more details about the challenges and opportunities in the 1G bioethanol production from Antonio Jose Vallespir, who works for Vertex, a bioethanol producer from Spain. And I will stop sharing my screen if I find the button.
Okay. I will try to share mine.
Yes.
I don't know if you can see.
I got it. So, Antonio.
Okay. You can see, and let me. No.
No, Antonio, we can see it.
Okay. Let me check. Yes.
Yes.
Now?
Yes.
Yes.
Okay.
All right.
All right. Okay,
Yes.
thank you. And I will introduce a little bit. We will see later in more detail the project that we have done in Salamanca in the consortium, but I would like to present now. Are you seeing the presentation or not?
We're seeing the
No.
PDF about the meeting.
No.
Now?
Yes.
No, it's okay.
Okay, sorry. So I will introduce a little bit in a basis bioethanol, and also why we think biofuels, in that case bioethanol, is so important or is going to play an important role in the decarbonation in Europe. Well, I will say that bioethanol importance in the near, medium, and long term is obviously secured by one, the growing global consensus for the need to reduce greenhouse gas emissions, obviously. Second one is, and this is something that we need to keep in mind, that transportation emissions contribute more than 25% of the total greenhouse gas emissions in Europe. And the third is that bioethanol, in that case, is one of the only proven cost-effective tool to reduce emissions in transportation. You can see on the bottom left that bioethanol provides more than 70% greenhouse gas savings if we compare with gasoline, but also with the electric car. And this is considering obviously the full life cycle analysis instead of the well to wheel. But and also on the bottom, on the right side, you can see that the cost of reducing emissions, for instance, E10 is more than 5 times less than the electric car if you consider a long range in that case. Well, just we will start saying that obviously bioethanol is a renewable fuel produced from crops that is then either directly blended with the gasoline or used as an oxygenator in gasoline production. And this is something that is probably the main use in the countries in the south of Europe, like Spain, like Greece, like Italy, and in the north member states in Europe, like Netherlands, like France, they use most the direct blending. Well, it's a very solid process, I would say very robust. It's based on fermentation. One of the flexibility that we have is that we can use all kind of raw materials that contain starch. Just to explain a little bit the process, these raw materials are crushed, heated, and treated with enzymes in order to release the sugars. Yeast is then added to start fermentations, converting the sugars into bioethanol. And after that, highly concentrated bioethanol is extracted by distillation. And the residual mass is dry to produce DDGS that is rich in proteins and fats, as you know, and is sold in the market as animal feed. And this is also something important in Europe because, as you know, probably 65% of the protein is imported today by Europe because we have a significant deficit in protein in the European market. Well, just to give an update about Vertex and the 4 facilities that we have in Europe, knowing that it's a carve-out coming from Abengoa Bioenergy in 2017. We have, Vertex has 780 million liters of capacity in Southwest Europe. This is all of the capacity in the region. And we have, I will say, a unique logistical competitive advantage. The first plant is Cartagena, that is the sole plant with direct access to the Mediterranean market. And for those markets like Greece, Italy, also Spain, that, as we have said before, they use mainly the ethanol as an oxygenator in order to produce CTBE instead of the direct blending. And you can see it's more or less is a facility that has been, we start operations more or less in 1999. Is today, I will say, we can produce 115 million liters. The nameplate capacity is 108 million liters. And also we have a cogeneration that is 22 megawatts per hour. The second facility, Coruña, that is well connected by road and rail to the Coruña refinery, and also good access to the Atlantic export in other Spanish ports like Petronor and also Huelva and Cádiz, in that case, refineries. Has been started operations in 2002. First, the nameplate capacity was around 150 million liters, but with a revamping today, the facility or the total production is around 185 million liters. And also we have a cogeneration that is 25 megawatts in La Coruña. Then Salamanca, that is a facility, is the only bioethanol plant that is located close to Madrid, and this plant is very competitive for the blending products, mainly in Spain and Portugal, because as you know, here in Spain, the distribution is through the operator named CLH that supply all gas stations across the country. And finally, LAC, our plant located in southwestern France, which is proving to be a strong and growing market. I think is probably the strong market in Europe regarding the direct blending. As you know, today, more or less, the penetration of E85 is around, I will say, 4.5% in the total pool gasoline. And E10 more or less represents or has a share quota around 50 to 52% in the total gasoline consumption. Well, and why bioethanol? And this is something that we have seen a little bit before, but transportation today makes up more than 25% of European greenhouse gas emissions, of which road transport makes up 70%. As we have said before, you can see that on a well-to-wheel basis, bioethanol provides more than 70% greenhouse gas savings if you compare with gasoline. And this is, as we have said before, considering the full life cycle analysis instead of the tank to wheels, considering the well to wheels analysis. As you can see, in Europe, more than 4.4 billion tons of CO2. That means in transport sector, more or less around 1.2 billion tons of CO2. Now we will see, I will try to highlight that why bioethanol. And in that case, is based on two factors. One, obviously, is regulations that is supporting biofuels, but also we will see that on top of regulation, the shift in gasolinization that I will say that we have experienced from 2015 with the diesel gates in that case in Europe. Well, you can see here that in Renewable Energy Directive 1 until 2020 and Renewable Energy Directive 2 until 2030, both of them have set ambitious targets for overall emissions reductions. You can see 20% by 2020 and 32% by 2030. But for us, the most important thing, and I will say, is not the overall target, is the specific target in the transport sector that today has been set in 14% by 2030, and this is a floor. From there, member states set the legislation for the local markets. Spain target for renewable energy in transport sector is 28 by 2030, and biofuels transport of 8.5% by 2020, that well above the 2018 level, as you can see. So for us, this is I will say, a tool that member states, in that case, has in order to comply with targets. Increasing the blending rate of bioethanol, in that case in gasoline, is, I will say, one of the easiest ways for member states to reach the emissions target for transport. But on top of that, and as I have said before, on top of regulation, there has been a clear shift towards gasolinization following the Dieselgate. You can see, and this is for Spain and for France, and this is an analysis that has been made by McKinsey. You can see in the middle column, based on that analysis, that the total car park of gasoline is expected to grow through 2030 in both markets, in Spain and France, but also in Europe. And on the right side, you can see that in those markets, total gasoline demand is projected to grow from 13.2 million tons to 15.2 million tons by 2030 in those markets that are the key markets for, in that case, Vertex Bioenergy. That combination of regulations and the projected growth in gasoline car park provides a significant increase on bioethanol demand in Spain and in France through 2030. And the same thing that we can consider for Europe. You can see in the Spanish market, more or less is around, I would say, 0.7 billion liters ethanol, and in the French market, around 1.3 billion liters. This increase in demand means that all our capacity will go to the local markets instead of exporting as we have been in the past. And the main conclusion that is Europe is short in bioethanol. However, domestic supply is expected to remain stable. And why? I will say that first generation plants have a complex licensing process with long lead times. And the second generation bioethanol technology, and we have the experience in Abengoa, in Houghton in the United States, I would say the second generation bioethanol technology is still pending to be proven at any commercial scale. Even if a new second generation investment is proven, a full ramp up will take at least 5 years to be ready. So that's why we think that today we have an ambitious target, but we need to, I will say, be in the same boat with legislations, because if not, we are not going to comply with the targets that the European Commission is setting.
Antonio,
yes.
Could you try to come to a end soon? Thanks.
Okay. Sorry. So what I try to mean is with that combination of supply and demand, it's easy to see that in Europe needs imports. Also, we have some limitations with imports. You can see here, one is the greenhouse gas savings that must be at least 50% based on the Renewable Energy Directive 2. Second is the arbitrage price that is today more or less the 20% of the price. Also strong markets in Asia, and also the seasonality for the sugarcane that is in countries like Brazil, the main importers from Europe. So this is how it has worked the market. Here, the only thing to say is that bioethanol demand in Europe, as you can see, is a narrow market, is around 7 billion liters. And how it has worked today, who is setting the price are the imports, and you can see some marginal players, and we will have, or price will remain strong during the next coming days, because, as we have said before, Europe is short in bioethanol. And in a last slide, and there is a conclusion, as we have said before, there is a global consensus for the need to reduce emissions. This is something that we have seen in the Paris Agreement. Bioethanol is one of the only proven and cost-effective tools to reduce emissions in transportation, as we have said before. And you can see that the car park in 20 years will be even stronger than is today, leading to long-term demand for bioethanol. And that's all, and we will see later with Juan Maria and Barbara probably the project that we have done in the consortium.
Okay. Thank you, Antonio.
Now, let me
for this very nice introduction of the bioethanol topic and the way you the way you see the bioethanol market and the need for addition or continuing biofuels production. Yes, just to meet the demand in Europe. So next up is Ana Isabel Susmonas Torres, who will present the case study of the retrofitting one of the bioethanol plants by a co-production of advanced biofuels. So the floor is yours.
Yes, I'm going to try to share my screen. One moment.
Are you still there, Anna? Your video is frozen.
Yeah, I'm not sure if she is frozen or not. It seems she has some problems. Yeah.
She must be frozen.
Yeah, I have the presentation. I can share it, I think.
She's
okay
back.
Now, Anna.
You
are
muted.
mute. We can hear you. Are you mute?
Okay, now?
Now,
yes,
yeah.
Now
Okay.
we hear you.
I'm going to try again to share my screen.
Yes.
Can you see my presentation?
Perfect.
Okay.
Yes.
Go ahead.
Okay. Hello, everybody. My name is Ana Susmozas from CIEMAT in Spain, and today I'm going to present one of the case studies carried out in the BioFit project, the bioethanol case study. First of all, I would want to give you a brief overview of the current bioethanol market. This figure shows the development of the production and consumption in the European Union. As you can see, in the last years, the bioethanol production and consumption is really similar and also increased but slightly. Regarding the share of bioethanol in petrol in the last year remains practically constant at 5%. In this slide, you can see the main raw materials used to produce bioethanol in Europe. Nowadays, most of the bioethanol is produced from starch and sugar-based feedstocks. And in fact, in 2020 in Europe, almost half of bioethanol was produced from corn, followed by wheat and sugar. The conversion of these raw materials is relatively simple compared to the advanced production processes, and there are well-established technology for the obtention of the corresponding sugar and to convert them into bioethanol. However, concerns on the sustainability of first-generation bioethanol, such as the use of food-related feedstock in the energy industry, the impacts on land use and the water resource, have promoted the production of bioethanol from lignocellulosic biomass. And why bioethanol from lignocellulosic biomass? First, lignocellulosic biomass is one of the most abundant renewable sources. In addition, these feedstocks are not linked to the food market, and many of them are residues, such as agricultural and forest residues from agro-industries, the organic fraction of municipal solid waste, etc. From a life cycle perspective, it usually presents lower CO2 emissions, and last but not least, it's possible to obtain different high added value products within an integrated biorefinery concept. The necessity of the transition from food-based biofuels to advanced biofuels is clearly recognized in the last energy policy measure taken in the European Union. In fact, in the context of Renewable Energy Directive 2, a 14% renewable energy target in transport sector is established, with minimum share for advanced biofuels starting from 0.2% in 2022 to 3.5% in 2030. In addition, this directive caps food-based biofuel to a maximum of 7%. Now, focusing in the BioFit project, the main opportunities for the retrofitting of first-generation bioethanol industry identified are the following. First, policies are the main driver to promote the transition from first-generation to advanced biofuels. Since advanced bioethanol production still presents uncertainties regarding its economic viability, the integration of second-generation technology into an existing first-generation facility could be an excellent option to ease this transition. In addition, integration of first-generation and two-generation technologies could result in some synergies such as the following. Taking advantage of the existing product distribution and feedstock supply and storage system, using the lignocellulosic parts of the sugar and starch crops, setting the purification areas, adapting the sugar content of the fermentation by mixing the mass, sharing the general infrastructure, and finally using the lignin as renewable fuel or even for high added value compost production. One of the main activities of the BioFit project is to develop a concrete case study, in this case for the retrofitting of a first-generation bioethanol facility. To carry out this case study, we work together with the following research partners, BEST, BTG, and CERT, and also with an industrial partner, Vertex Bioenergy. In this slide, you can see the methodology used to address this case study. The first stage is the project description. Here, we have collected all the relevant information to carry out the case study. This information includes market situation, the location, inputs, outputs, etc. In this project, all the information related to first-generation bioethanol production was supplied by Vertex Bioenergy. And in order to obtain the necessary data of advanced bioethanol production, we have modeled the retrofit case using process simulation tools. In this project, we have used the software Aspen Plus. And through this software, we have been able to obtain the mass and energy balance for calculating the raw materials, consumables, utilities, and energy requirements. Once all information were collected, a techno-economic assessment, sustainability assessment, and risk analysis were performed. In this project, two options for the bioenergy retrofitting of Biocarburantes de Castilla y León facility were established. This facility is one of the Vertex plant and is located in Bavilafuente, Salamanca, in Spain. In this slide, you can see a picture of Biocarburantes de Castilla y León plant. This plant used corn grain as feedstock, obtaining ethanol, DDGs, electricity, and CO2. In this box, you can see the amount of feedstock and products obtained. In this slide, you can see a simplified diagram of the production process of this facility. First, corn grain is cleaned and milled, and then is mixed with water and heated with steam prior to enzyme addition. This process allows the conversion of starch polymers into free sugars, and then these free sugars are fermented in order to produce a rich ethanol stream. This stream is subjected to distillation, producing high purity ethanol, and the remaining distillate is used to produce DDGs. In order to fulfill the energy demand of the plant, this facility has 3 natural gas boilers producing all steam required for the process. This facility has a gas turbine, also has a gas turbine where electricity is produced. The resulting gases of the gas turbine are used to dry the DDGs, and the electricity produced is sold to the grid. In this slide, you can see the retrofit case A defined in this project. In this case, we have considered the production of 11,000 cubic meters per year of advanced bioethanol using an industrial waste from a yeast production plant and wine alcohol as feedstocks. Both feedstocks are subjected directly to distillation in the ethanol recovery area of the first generation facility. As you can see, this case presents low technical complexity, and therefore it will have a low CapEx, and it will be quickly implemented. In this slide, you can see the retrofit case B. In this case, in addition to the production of 11,000 cubic meters per year of advanced ethanol from an industrial waste and wine alcohol, 19,000 cubic meters per year of advanced ethanol are also produced from corn stover using second generation technology. To do this, first corn stover is pre-treated in an steam expression unit, obtaining 2 streams. The first one is a water insoluble solid fraction called waste, consisting mainly in glucose and lignin. The second fraction is a liquid fraction which consists mainly of xylose. The waste fraction is subjected to a pre-saccharification and simultaneous saccharification and fermentation processes, obtaining an ethanol-rich stream, and this stream is concentrated to about 50% in a distillation column. The remaining stillates, together with the prehydrolyzed fraction, are mixed with the first generation stillates in order to produce DDGs. On the other hand, the ethanol-rich stream for the second generation process is sent to the ethanol recovery area of the first generation facility in order to produce high purity bioethanol. In this case, you can see that present higher technical complexity, and therefore it will have higher CapEx and longer duration. In order to evaluate this case studies, an economic assessment and an environmental assessment were carried out. In this slide, you can see the main results of the economic assessment. The figure shows the influence of the advanced ethanol price in the net present value and in the internal rate of returns parameters. As you can see, the advanced ethanol price has a great impact on the economic viability. In fact, in case A, a price below 750 euros per cubic meter could result in a negative net present value. We can see also that better results are obtained for case B than for case A. This is in terms of net present value. This is due to the higher production of advanced ethanol in case B. In terms of internal rate of return, you can see that the increase of this parameter is much greater in case B than in case A than in case B. This is due to since the investment required in case A is much lower than in case B. And finally, other important result obtained through this assessment is that the yield of advanced ethanol has a great impact on the economic viability. In this slide, you can see the main results obtained through the environmental assessment. The first figure shows the contribution of each case to different impact categories. As you can see, current state and retrofit case A, present and retrofit case A present similar environmental behavior in all the categories. The retrofit case B presents the highest contribution to the climate change impact category, but the lowest impact in the rest of the categories. This high contribution is due to the retrofit case B presents higher energy demand, mainly linked to the second generation technology. In the second figure, you can see the contribution of the specific processes to the climate change category. In this category, you can see that natural gas, both in gas turbine and in the boiler, is the responsible for the most significant share of this category. Finally, the main risks related to the retrofit of first-generation bioethanol industry are shown in this slide. The table shows the risk in order of importance, the probability, the consequences, and the total risk score, and also the main mitigation actions identified. As you can see, the main risk identified is the change in regulation. This risk generates great uncertainty to decide a possible investment by the biofuel industry. Also, the risk could be mitigated through the diversification in products such as bioethanol first and second generation, industrial alcohol, etc. The next risk in order of importance are the following: decrease in support by biofuels compared to other renewable sources, such as the renewable electric car or hydrogen, the raw material supply, variability in the price of raw materials, the raw material storage and the safety stock to maintain this production, safety in raw materials storage, the decrease in fuel use caused by a decrease in the mobility due to the pandemic, and finally, the risk in the process due to efficiency issues. In contrast to first-generation bioethanol production processes, advanced bioethanol production usually shows less conversion efficiency, and therefore it's important to continue promoting the investment in R&D and in this field. This is all from my side. Thank you very much for your attention.
Thank you very much, Anna, for this nice presentation of the case study about the integration of lignocellulosic ethanol into first-generation ethanol plant. We will then move on directly to the, so if there are questions, we will keep them for later for the question and answer session, so that we can move on now with the second case study, which will be presented by Andrew Hull from Swedish Biofuels, and it will be about the integration of alcohol to jet into a first-generation ethanol plant. Andrew.
Arne, thank you very much. Morning, everybody. Thank you for this opportunity to present the results from the case study. As Arne said, it's a retrofit for a 1G ethanol plant, and in fact, it's the basis for this is the Vertex plant, which has already been introduced earlier. So first of all, I thought it would be good just to look at the ATJ process. ATJ stands for alcohol to jet, and it was originally developed by Swedish Biofuels, and the patent actually dates from 2004. The patent itself actually concerns the production of jet fuel from biomass, in particular lignocellulosic biomass and other types such as grain. But for quite a long time now, we are focused mainly on the end product, because it is actually the jet fuel which is needed in the market. And so on the left-hand side of these diagrams here, we start off from an alcohol, because there are, as we've heard, there are many extremely competent companies which are capable of producing ethanol, isobutanol, or even mixed alcohols, C2, C5, for then to be finished in this process, which we call the ATJ SPK process. SPK stands for synthetic paraffinic kerosene, and it basically consists of dehydrating let's take ethanol as the example, dehydrating ethanol to ethene, which is the C2, oligomerizing that to isoolefins in our process, and it could be other types of olefins, could be N-olefins and so on, and then hydrogenating those and fractionating them to produce ATJ SPK. The fractionation results in other co-products which are not shown in this diagram. So standard diesel, in Swedish Biofuels case, standard diesel.
Excuse me, Andrew?
Yes?
Excuse me, it seems there is a really strange sound, like an engine something. I don't know if it's in your...
Yes,
I can hear you very well.
You can hear me, can you? Or you can't? Can you hear me very well or not, Rachel?
I can hear a very, you know, a strong noise. I don't know if the rest of the audience can hear it.
Right, Andrew, I can take it from here. So if you will, Andrew, can you hear me?
Yeah.
Yep.
Right, I can take it from here. You can put in mute. Sir, we apologize. We do have we're in different places, but Andrew, where he is, we have a construction going on, and we asked them to call to hold it for an hour. But unfortunately, this well, the presentations was of people before, they were longer than we expected, so it was running over time. And for that reason, unfortunately, we can't still ask people to keep the construction going on. So this is going on. So I will try to take over. It's not my presentation, it's Andrew's presentation, but I assume I know a little bit about what we've been doing. So this slide is showing our Swedish biofuel ATJ process, which is been already certified by ASTM. And so one is a pathway which is certified already is ATJ SPK process, which is not including aromatics. And aromatics very important for the certification of 100% jet fuel, which means that to replace 100% of fossil fuel to sustainable biofuels, we will need to have an additional certification, including aromatics. And this is what Swedish Biofuel is in the process, and we hope that we're going to go to balloting this year already. So we're leading this certification. We also have done we're also working on the different feedstock. We're extending our feedstock from sorry, with additional alcohols, which is give us opportunity to introduce other raw materials of waste of, for example, ethanol production, like carbon dioxide. Within this study, we didn't look at these feedstock possibilities for simple reason that to produce to use this CO2 as a feedstock, we would need to have an additional hydrogen, which are many companies pursuing right now and producing hydrogen from electricity. So, but seems like we will talk about it a little bit later. Electricity, green electricity is not available in present site, so we decided not to do this this study. So anyway, this slide just an overview of potential for Swedish biofuel technology to introduce jet fuel, which has a potential to be certified as a 100% replacement of fossil fuel. And our pathway obviously starting from alcohols, which call ATJ, and that's why we were doing retrofitting on existing first generation plant of in Salamanca. So next slide, please. So the current scenario is that it's showing on this slide. So ethanol is we heard more a little bit earlier on the plant, and is for the moment at this stage is producing first generation ethanol from grain. We know, of course, that there is a serious drive of the European Commission and community to introduce biofuels over second generation alcohols. But for the moment, there is still this first generation within the current scope. We have, for example, gasoline ethanol mixtures based on first generation ethanol all over the Europe. So for the moment, we are allowed to use this ethanol, and it's all down to final user, the passengers, whether they would be happy about that or not. So, but still, to compare to fossil crude oil, I think that would be a great first step forward to have jet fuel, to fly on a sustainable jet fuel, and if there is availability of grain, which is we still have in Europe, and it's less competition with food, so it's better to use that than fossil kerosene. Next slide, please. So this is what we were looking at, the retrofit scenario, and so we were focusing, of course, on production of our new upcoming certification to produce jet fuel with aromatics using ethanol from the plant, and with the new certification to be able to have the 100% replacement on the market. So diesel is also used in this particular scenario, and because this diesel is a bioproduct, and gasoline, in fact, is a bioproduct of our technology, our process. And within this scenario, we were using diesel as an additional product. Supporting the business case. But part of the ethanol within this case is used for pumping alternative engines, ethanol engines, or to use it as a blend, ethanol gasoline blend up to 5 to 10% as a blend for standard spark ignition engine. Next slide, please. So Andrew, is it got quiet on there? Because I got a message that they stopped the noise at this moment. So would you like to take over from me?
Unfortunately, it's still there, but I will take over as soon as it's finished.
All right, very good. Right. So are we using the same slide, or it's or you changed the slide? Sorry.
This just shows the alternative scenario where you have separated plants. So
all right. Yes. Sorry about yes. So so we've been looking at two scenarios. One is the building our ethanol to alcohol to jet plant directly at the site of Salamanca, and the second alternative scenario, whether we build the alcohol to jet fuel production plant separately close to the airport. And this is in fact what Swedish Biofuel is right now doing in Sweden. So we're building independent ATJ production plant close to the airport, and we will be delivering ethanol to our site. It will be slightly different because we will be using second generation of ethanol, and we also have green electricity available at this site, which is slightly different scenario in scenario which we have in Salamanca or in Spain generally. So, and you will see the results, the effect of green and black electricity at the end of this presentation. So, two cases been looked at during our study. Next slide, please. Right. So we've been sort of, this is just an overview of a supply chain. This is the way we're looking at the sort of retrofitting the existing plant, where we will be using partially of existing infrastructure to contribute to the production of construction of ATJ plant, which we expect that we were expected that it would have a little bit better capex for economy on a capex would be better. Of course, it will be OPEX will be better because it can be shared operation as well. And also we were expecting to have better environmental impact. So life cycle analysis, we were expecting to have better. So that's the steps where we see in the overall diagram where we see in the ethanol production. And then we've been also looking what is the happening if we have a lignocellulosic feedstock, and then additionally putting our, which is on the right side where we producing jet fuel. So it's a little bit here, you see diesel naphtha. We do not really produce diesel naphtha within our process. We produce in standard gasoline, EN590, and we produce, standard diesel, EN590, and standard gasoline and standard jet. So, which is important for our sort of when it's when we have we're building ATJ production, when we're using just ethanol without CO2, we're not required an additional hydrogen. So the hydrogen which we're using within the process, produced within the process, and obviously is green hydrogen. But if we would use this, what we were planning in the future, to use CO2 from ethanol production, which is obviously produced during the production of ethanol, then we will need an additional hydrogen, and then we were looking, of course, for green electricity to produce that hydrogen, additional hydrogen. Very good. Next slide. Yes.
Okay, you have a couple of minutes left, but
right.
Just want to let you know.
Very good. I will try to be faster then. Right. So we've done the market assessment, the feedstock availability, which it shows on the graph on the right. In fact, I'm sure you've seen this graph many times on different other presentations. So we don't see that there is a feedstock problem for production of alcohols in Europe. But of course, there will be a rather high demand, and it will be price of the feedstock for production of alcohols will be affected by high demand of SAF. Next slide, please, Andrew. So we've done technical economical assessment. Andrew, I would like you to take on this slide, please, now.
So I'm sorry about the buzzing wasps that you have in your ears. So quite simply, the main result from the economic assessment is that the internal rate of return is expected to be around 30%. That's you can see from, well, you can derive from this graph here. The blue bars are the cumulative of the revenue, which is the orange bars, the net cash, rather not revenue. The net cash is the orange bars, and the blue shows the accumulation of that. Of course, there are many considerations. One of those is the volatility of the oil market, which has recently gone up quite considerably. Also, the SAF has increased in price over the last 9 months very considerably, much more than the oil. And of course, there are changes in feedstock costs, and the stability of the policy framework has an immediate effect on everything. From the environmental point of view, the baseline scenario shows emissions per megajoule of fuel of 53.26 grams CO2 equivalent per megajoule, and the saving compared with RED II is 43%. When you retrofit the scenario based on these results here, then there is little change. Of course, the emissions couldn't be reduced. Well, they seem to be actually. Well, there's a slight change in emissions, has been reduced slightly, but we can think of those as essentially the same. And the saving with regard to RED II is also essentially identical. What happens though when you have a sustainable retrofit scenario? By sustainable, that means that the sources of energy, electricity, and also heat for steam, when those are sustainable, renewable, then the savings compared to RED II are quite substantial, 95%. It's remarkable. And in the alternative scenario, the numbers are pretty similar. And here we see the sustainable alternative scenario, the savings compared to RED II with green electricity and green sources of energy for steam is it's also 95%. There are some risks. In fact, the team considered a total of 13 risks, which you can see on this chart here. The main risks are that number 1, 4, and 6, that if you're using first generation alcohol, and this refers to the previous slide, then of course the ATJ kerosene might not be considered to be of the right category. This risk would be mitigated by going to 2G ethanol, and a lot has been said already during this session. The risk number 4 is that the sustainable feedstocks will have increases in price. That is only mitigated by the increasing price of SAF, and we expect that these prices will go in the same direction. McKinsey also seems to think that, and many others also. And then finally, again, relates to the previous slide, if there's unsupportive or short-term policy frameworks, then that is also a major risk. We consider, though, that people are quite convinced, the populations of Europe are quite convinced that this is the way forward, and so we're not really expecting that to happen. Key performance indicators, already been through that, that the carbon dioxide emissions can be reduced by 95% if there's a sustainable energy, if the energy supply is sustainable. And this basically comes down to the fact that Swedish Biofuels 80-day technology is greenhouse gas emissions neutral. There is the possibility of achieving negative carbon emissions if the side streams between the two plants are connected more closely. Angelica already mentioned that the CO2 from the fermentation can be incorporated into the Swedish Biofuels process. This is probably the biggest, would have probably the biggest effect on the emissions, and we expect then, in this case, that we could even have negative carbon emissions. And all this for a jet fuel, which gives 100% replacement for fossil jet fuel. And here, Arna's already showed this photo, but this is a test from a year or so ago at GKN Aerospace. I included it because it looks very pretty. Main learnings. From the technical economic assessment, revenue is much higher than investment. We're actually, for us, making huge amounts of money is not the driver. And I think for many of us, it's not the driver. Of course, for investors, it's the driver, so it's important to have this. But we are trying to fix the problems that we have with the environment. That is the main driver. There is large demand for SAF, and according to the results of the study and other studies that we have conducted independently, there is sufficient feedstock availability. And finally, on a sustainability assessment point of view, the CO2 reductions will be almost 100%. It is, of course, important to recognize that renewable energy supplies are important at all stages of production. And I think that's actually quite obvious, but it is worth restating. we would like to thank the hard work from the whole team. Names there, I hope I haven't forgotten anybody. And thank you very much for this opportunity to present to you.
Thank you very much, Andrew, to present the nice results of this case study. Discussion later. Now let's move on to the next speaker, which is Stefanie Hauschild from BioFIT, who will talk about some other technical options for retrofitting and some policy recommendations. Stefanie.
Yeah, thank you very much. And actually, I'm not sitting next to Andrew, but I also have a construction site next to my window, and I really hope that you can hear me properly. And,
tell Angelica to send them an SMS and they'll stop.
Yes, would be perfect. And I try to share my screen now. Can you see my presentation now?
Yes.
Yes, but in we see your now it's better.
Now it's in the presentation.
So thank you very much for the introduction and also a warm welcome from my side. I'd like to shortly present you some BioFIT activities and results, namely the technical options and policy recommendations for retrofitting the first generation BioFIT sector. And for doing so, I think it's worth looking at our survey, which we have conducted some years ago on drivers and barriers for retrofitting. And because this is mainly the basis for our discussions and for preparing these technical options and preparing the recommendation files. So we conducted this survey as an online survey among non-retrofitters, which are mainly companies who haven't done any retrofits before. For sure, the survey was open for experienced retrofitters as well, but we asked the participant of the survey to decide whether they see as a non-retrofitter or experienced retrofitter in order to evaluate the results separately. And the first generation BioFIT sector was for sure not the only sector we addressed. It was for all sectors, but we could divide the answers as well. We have categorized our arguments into 4 aspects: the technical, economic, environmental, and political aspects. And within these categories, we stated different arguments and asked the participant to rate the relevance of these aspects in terms of with respect to the question whether they would retrofit or not. And below on the slide, you see let's say the top 6 results for drivers and barriers of the oval sections. But we realized that especially for the technical drivers, the sector-specific answers were different. So I think it's worth looking at the biofuel sector itself. Here on the left-hand side, you will see our summary of the results for 3 different sectors. The green one is the first generation biofuels, and the picture is about the drivers. And you can see the arguments we stated and also the rates of the participants. And you can see that especially for the first generation BioFIT sector, the higher flexibility of the plant and diversification of the product portfolio are main drivers, or are named as the main drivers, and supportive to foster retrofitting measures are also the existence of experience in the company and for sure the bioeconomy strategy of the company itself. And it was also named that, which is for sure not very clear, that implementation with could be, or measures which could be implemented very fast, are more favorable than these ones, which take a lot of time. With a special look on the barriers, you can see that especially the political category is of main interest, and the unstable regulatory framework and the missing coordination between the EU and national policies were named as very important barriers, which does not mean that we have this situation at the moment. As Anna already told, we have a highly regulated industry. The biofuel sector is highly regulated, but these arguments are seen as a very strong barrier if, for example, the regulations are changing constantly. And furthermore, apart from the political issues, you can see that a limited availability of the right amount of biomass is also often highly rated argument within these barriers. And with this in mind, so the drivers was the flexibility of the plant and the diversification of the product portfolio, as well as the barriers I just named. We can have a look, or we could have a look within the BioFit project on different technical options, which we also discussed during our industry forums and our sector recommendation papers. And I would just name some. Here you can see some examples for the ethanol industry. We just heard the first two of them. So the use of lignocellulosic feedstock, or the use of the produced ethanol to produce synthetic paraffinic kerosene, or even further to kerosene with aromatics. But we just heard that. I don't want to go in detail with that, but we have for sure some other possibilities. Just to name one further, it's the separation of CO2 from the fermentation of gases, for example, in order to use these CO2 as a biogenic resource for further processing, not only in the food industry, but also, for example, in power-to-liquid production plants, or as a resource for algae cultivation. But, and you have to always consider that, even though CO2 separation is quite good developed and state-of-the-art for some fermentation plants, if you want to have a subsequent technology, or if you want to implement an add-on, the technology readiness of the overall plant is dependent on this technology you add. So if you want to produce liquid fuels, for example, from the CO2, you have to consider that the technology might not be as highly developed as the CO2 separation itself. And very shortly, some examples for the biodiesel sector, which might be relevant for as a retrofitting. And I just want to say that we will have an expert here today in the round table. So if any questions arise with regard to the biodiesel sector, I'm happy to direct that to Edgar Ahn today. But just to name some, very often discussed is the multi-feedstock plant. So to temporary switch from vegetable oils to used cooking oils or animal fats, with all the challenges and problems we can discuss with regard to this feedstocks, I think it might be a very good opportunity to broaden the feedstock base, even though technical adaptation are quite challenging, especially for the pretreatment unit. And it might not be the best option for every plant, especially if you look for look at quite large plants, you will have trouble to receive the amount of feedstock you need. Or if you have a pharmaglycerol upgrading, for example, which is also retrofit, it might not be the best option to use Tuco. But having pharmaglycerol upgrading mentioned, this is for sure a retrofit. But you can also use glycerol to convert it to other chemical products, to other chemical platform chemicals, for example. And I just named one, methanol, where you convert glycerol to syngas and then synthesize it to methanol. This is not it is not the highest developed technology, but one option, and it might open the discussion for other platform chemicals. And for sure, the biodiesel sector can be retrofitted in terms of the reactor design and the use of biobags, auxiliaries, or the change of energy sources, like the change from natural gas to methane. But time is running, and I know we would like to go into the roundtable discussion. Let me shortly go to my last topic, the policy recommendation. These are not only recommendation directed to the policy, but relevant for them, and also relevant for research and for funding authority, for example. And we have divided these recommendations into 4 different columns or categories. The first one is for sure the feedstock, which was also named in our survey as one big driver and also barrier. We need to broaden the feedstock base, look also to currently underutilized feedstocks or contaminated feedstocks. We have to think, or we have to make the collection systems better, and also the documentation systems, which is very important to prevent misacting, let's say. So this is a big topic in feedstock field, and the feedstock leads us to the technology, and a statement which is very often done in the biofuel sector: keep your technology openness, especially for the biofuel sector. This is very important because the biofuel sector is very diverse. We have different products in this sector. We have different technologies. Not every retrofit is suitable for every plant size or plant constellation, for every feedstock, and also for every investment volume you want to take in your hands. And with investment, we can go to the 3rd column. It is the situation with the biofuels market is that it is still a quite young industry in comparison, for example, with the refinery market. So a lot of plants have been installed after 2000, 2005. So it is not so common for such young plants to invest in high volume or highly costly installations. So it's very important if we want to keep the plants to keep or to stay with very good funding schemes in order to develop the technologies for retrofitting, and also to give them the possibility to implement these retrofits. And last but not least, and this is, I think, one of the biggest barriers stated not only in my presentation, but also in the presentations before, also in the pulp and paper session. We need clear, stable, and ambitious long-term framework conditions for the plant owners and companies, so that they are willing to invest, that they are not that they are willing to take money in their hand to change or to retrofit their plants. And one point which has risen or has come up quite often also in our industry fora is that the industry is sometimes not only confused, but is wishing a coordinated national decision, especially with regard to the feedstocks in Red 2 Annex 9 Part A, with regard to the feedstocks which are used to produce advanced fuels. As Red 2 is for sure giving the framework, and national policies are able to decide on within this framework which feedstocks are credible for that and which not, which means that for different national policies, the feedstocks are sometimes credible or not. So that was seen by the industry. That was the result. These were the results from our survey, and with these somehow political recommendations, I will just take the opportunity to advertise our policy breakfast tomorrow, and I hope you join us. Take a cup of coffee and take the opportunity to discuss not only the first generation biofuel situation, but also the other sectors. And with that, I'd like to hand over to Anna for the roundtable discussion.
Yes, thank you, Stephanie, for this sum up and a short preview of the session tomorrow. So I think we have seen all of the presentations, and we are now here for the discussion. So Raquel,
yeah.
You want to take over for the discussion?
Yeah, thank you very much, Arne. I think we are a little late, and now we have prepared a roundtable around 30 minutes duration. Speaker, panelists, audience, thank you very much to attend this event. We prepare some question. The audience can use the chat if you want to, just to make the query or the question you want. And just switch on all the cameras of the panelists. The roundtable includes the following panelists in addition to the speakers. We have Antonio Vallespir, who has already been introduced, of Vertes. Manuel Bustos is the Biofuels manager at APA, is the Association of Renewable Energy Companies here in Spain. This association put together companies and entities that use renewable energy sources. Also, we have José Ramón Freire. He's a specialist in renewable energy and alternative fuels. He's a general manager of the Spanish Ethanol Association called BOE. We have also the Andrew and Angela who have already been introduced. Edgar is with us also, Chief Innovation Officer at BDI. They have been researching and developing new technology to get biofuels, and he's also part of our advisory board here in BioFit project. And with any more delay, I think perhaps it's good to start with Edgar, because we all during the session speak a lot about ethanol market, and perhaps it's good to know how is the situation in biodiesel market at this moment. Edgar, please.
Thank you very much, Raquel. Before I answer your question, I only want to take the opportunity to thank the whole BioFit team for the excellent work. It was a pleasure to work together with you in this 3 years project, and I think the results show for itself. It was a very successful project. What is going on in the biodiesel market at the moment? In Europe, we are still at a very high level of production, still mainly based on vegetable oils, but on the one side politically driven, but also on the other side from an economic viewpoint. A lot of projects, new projects, are mainly based on waste-based biodiesel, be it based on cooking oil, be it based on animal fat. There are still new projects. Our company has just had 2 new projects in Europe, with each 100,000 tons year capacity. So there is still a growing interest in waste-based animal biodiesel. And from this change, so to say, within the biodiesel industry, coming from vegetable oil to waste-based biodiesel, there is a lot of retrofit projects going on in this direction to change, as also Stephanie showed in her diagrams and in the table. The main focus in retrofitting first-generation biodiesel plants is to increase feedstock flexibility, to make the plants capable of taking in waste material in a portion or be changing it completely to waste-based biodiesel. And I'm very proud that also one of our projects is also documented within the BioFit fact sheets, where you can see all the details of the project where a rapeseed oil-based biodiesel plant was changed completely into a waste-based biodiesel project, and all the details can be seen there.
Okay, great. I was mute. Thank you very much, Edgar. It's so the technical option, the most relevant in the biodiesel industry. What do you think is the most relevant at this moment?
At this moment, I think certainly the tendency is to change feedstock and to change to a waste-based feedstock. New technologies are on the market, enabling you also as a biodiesel producer to take in even worse feedstocks like sewage residues, trap greases, all these kind of really ugly feedstock. Therefore, technology and proven technology is available. But what I think is also important to mention in the Retrofit project on the first-generation biodiesel is you're not only changing the feedstock, you're also changing the business case, because you're changing from agriculture-driven, so to say, business case to a waste-based business case. And this is sometimes the hugest obstacle for biodiesel producers from first-generation biodiesel.
Yeah, for sure. Just for all the panel, what do you think about this feedstock competition between different biofuel sector? What do you think?
Well, if you want, I can speak about that issue. Well, I think that the first generation bioethanol has demonstrated that don't compete with food, and increase the competitiveness of agriculture and livestock in the European industry. I think that this biofuel has one important difference from other biofuels is the simultaneous production of food. And this also help to reduce the price of animal feed, the imports of protein from outside the European Union. And I think that it's very important to help to make decision of administration and to develop the consumption in the European Union, because with this market, with this develop of the market of the bioethanol, we can also found investors in the second generation in the industry.
Yeah, sure. Arne, please.
Yeah, maybe just an opinion, because I think the change of feedstock base from agricultural feedstock to residues, however, this is very much policy driven, in my opinion. If we compare the biofuel sector to some other sectors that we have looked into in the BioFit project, they are different, because the retrofitting in fossil refineries and in fossil firing, for example, there, if you do bio-based retrofits, you have additional bioenergy in the end. In our sector, in the biofuel sector, we already have bio-based products to start with, and the products that we start with, they already have very good greenhouse gas emission savings, and they have improved themselves. So in my opinion, it is not so much of benefit to change the feedstock in industry that is needed to produce the vast amounts of renewable fuel that is needed in the transport sector. So if we do a lot of efforts in changing the feedstock from agricultural feedstock to residues with the plants that we already have, in the end we end up with the same amount of biofuel and we don't have anything additional. So I think it is much more interesting in the end. It's also kind of a lesson learned from this project to foster build-up of additional facilities rather than changing the feedstock in the existing facilities from one feedstock to another. So this is maybe a very general comment to this question.
Yeah, but very, very interesting, because I think the feedstock and the cost, and even if the market suddenly go to the waste market, or just to change all the feedstock, perhaps really have problem with the price of the feedstock or feedstock competition. What do you think, Emmanuel, about it?
Yes, I fully support what Edgar has said. I mean, the experience in the biodiesel sector in Spain is that many plants are already making this retrofitting in order to widen the type of feedstocks. I mean, in order to make possible to use waste and residues. This is obvious a regulatory driven change. As long as first generation feedstocks are limited, not only limited, but it seems that at some point it seems that they are going to, especially those in the with high ILUC impact, they are going to be phased out for the biodiesel sector. I mean, so it's, I mean, retrofitting for widening the scope of feedstocks it's the only way to survive for biodiesel plants, because as it has been seen in the interesting presentations on the bioethanol retrofitting, you can see that that for current biodiesel plants is not possible retrofitting to for producing biofuels for the aviation sector. You know, so something that it's possible, as it has been explained, for the bioethanol sector. So this is, I mean, this is an important difference between biodiesel and bioethanol plants. I mean, the important demand that will come from the aviation. I mean, it would open for the bioethanol sector and for producing ATJ is a very interesting opportunity if this retrofitting is possible.
Yeah, sure. Here I have a very pertinent question for all of you. Start with Edgar. I don't know. Do you think if I mean, do you think it's a good idea having different target for biodiesel and bioethanol in the regulation framework? What do you think?
If I may start, it's a good question, which I never thought about. I have to confess. But I think so far, as these are so different sectors, also in the transport.
Sorry, Edgar, I don't know. Someone is speaking. Please mute the micro.
I have to share the office. Okay.
Okay.
So I think so far it always went very well to have different goals, be it in bioethanol and be it biodiesel, because they are so separated transport sectors, so to say. So I don't see any benefit not to have something like that. I see it more difficult, this is my personal opinion, with the capping of different types of biofuels, where I sometimes really have difficulties to understand why are we capping a kind of biofuel which is successful? Why do I put a limit in it? So this is something which I don't understand. I would like to have an explanation for.
Yeah. What do you think, Antonio, about just have to target definitely for
Yes.
ethanol?
In my opinion, this is something that we are fighting today because we think it's very important if you want to deploy, for instance, in Spain or countries or member states like in the south of Europe, E10 or E85, because, I mean, I'm in favor to provide flexibility, obviously, to the oil companies, but I think a minimum target separate by product, I think it will help a lot in order to deploy direct blending. Because if not, they will also use, in order to comply with the mandatory target, the economic one. In that case, in Spain, they are using mainly the ethanol only to produce ETBE as an oxygen, but they are not deploying E10. And this is something that you can see in our country, in the next country like France, that is the opposite. You can see in France that today, more or less, E10 represent around 52% of the total consumption, and in Spain, it's 0.
Yeah.
So I think it's important.
Okay.
But also I agree with Edgar regarding the capping. It doesn't make sense to cap all first generation biofuels because it has been introduced in 2009 because the threat of the ILUC, and this is something that today the European Commission is evaluating, and as we know, is a high risk ILUC study, this type of thing. So in my opinion, this is something that they need to remove. I know it's something difficult to do because one, you make a step forward, it's difficult to remove the cap, but I think this is something that obviously doesn't make sense.
Okay, thank you very much, Antonio. We have some question on the chat. Alejandro Fresnada Cruz, I think it's for you, Antonio, regarding RED 2, second biofuels production objectives. Are there find the same technological barriers for other biofuels as FAME as for bioethanol?
Well, I think second generation in bioethanol, and this is something that, in my opinion, here in Europe, we have two issues with the second generation. One is that technology is still pending to be proven, and this is a reality. We have experienced this with 3 projects in the world. I remember Poet, the other one DuPont, and Abengoa in Hugoton. And this is something that today is still pending to be proven. And also, I think here in Europe, we have another issue or another problem that we need to face, that is the availability of the biomass. In order to be or to make a project feasible with a real cost. I remember in the States when we started the project with Hugoton, I remember that all the models, the economic models, say that we need a biomass around 40 euros per ton in order to be able to make the project profitable. And I remember also that it was not an issue, the biomass in the US. In Hugoton, in Kansas, where we were, something that we don't have any problem, whatever. And the reality, when we start, is that the biomass put at the plant level was the price more or less around 100 euros per ton. So even today, technology was a reality, we will see a huge problem because I think today enzymes and everything is not ready in order to produce in an economic way. And this is a reality because we have experienced this in Hugoton, in the Abengoa facility, but also in DuPont and also in Poet. Okay. So I agree that we need to move forward with the second generation, but one important thing that I always say is that in order to evolve second generation, we must preserve or we must support 1G, because the only players that will invest in second generation will be the players that today are in 1G.
Okay, thank you, Antonio. Some question? I can hear someone. I have another question on the chat is, which is the state of the market as far as you know for bio-heavy oil as bioproduct of a second biodiesel production? Edgar or Manuel?
So I only can say for our technology that when we are retrofitting to a multi-feedstock plant, all the side streams are used either internally as a heating agent or generating the steam, for instance, for our production. But this is for, so to say, second generation, as we call it, second generation biodiesel production. I'm not the expert.
Okay, thank you, Edgar. Manuel, do you want to say something?
Yeah, regarding bioheating oil was I think was the question.
Bio-heavy oil.
Bio-heavy
oil.
Bio-heavy oil.
If Alejandro want to explain better the question. Alejandro, are you there?
That can be a residue from distillation of in case of using waste feedstocks.
Yeah, so as far as I know, bioheavy oil is, as you say, a residue from distillation, the biodiesel, when it's produced of wastes as used cooking oils.
So
yes, we have seen
our burners. We use it internally in the farm, so it's not the.
Edgar, we couldn't hear you very well.
So I just wanted to repeat this bio-heavy oil, as the questioner asked. We use it as the residue from the distillation process is used as a heating agent internally in the biodiesel plant to generate the energy. So it's not a waste stream, it's used internally, or could be sold as a heavy oil.
Okay. Okay. So I moved now. If you want just more two questions for Bertes, for instance, if Barbara or Antonio, the suggested retrofit option and result of the case study fit to your expectation? Barbara, Antonio?
I think Barbara.
Yes, I'm here. Sorry, I was muted. I think that the first thought that we had when we started this collaboration with the CMAT more or less have been reinforced, because the challenges as are the ones that had been discussed here, everything regarding variable regulations, the way the European directives are being transposed into the different countries. For instance, the production of ethanol, double content ethanol, the waste that you used is not considered as double content in all the countries. It depends on the country. So our first thought is that the retrofit that involves the less capex, in this case, the one that is been focused on using wastes as wine lies or other waste from containing ethanol, are the ones that look the better for us. And in case of a second generation retrofit, as Antonio just has explained, the thing is that we have our past with Abengoa. We know the technology is not as proven as it should be. So for us, the decision to invest in this is much harder. Okay.
Good. Thank you, Barbara. Another question for Andrew, just to change to the jet fuel. With a critical view on the case study, do you rather pursue the integrated approach, or would you now prefer a standalone unit?
Oh, excuse me. I had an answer prepared for this. It went to the wrong place. So, oh, it must be the right place. You see a PowerPoint slide.
Yeah.
So, integrate or segregate?
Yeah.
I'm calling this question. Sorry about the play on words there, but I couldn't resist. So, with regard to what to do, which way to go, we've seen that, in fact, the main considerations relate to the energy mix and how that is distributed within a particular country. In Sweden, we're quite fortunate in having large amounts of green electricity, which arises partly because of the huge size of the country and the relatively small population, but also the large number of hydroelectric plants and so on. Even though I understand that those are up for grabs by RED 2 or RED 3 or whatever. But never mind, let's try not to avoid too many divergences. So green energy mix first, and then transport distance is the second. But at this stage of the market, transport distance, it's important, but it can be mitigated by basically putting plants close to in terms of jet fuel, putting it at airports and things like that, so that the distance in the end doesn't really affect things much. With integration, as with all integration, the possibility is that you can amalgamate streams, depends what the streams are, and we briefly touched on a couple of streams which are possible to incorporate between the Vertex plant and our plant. The use of carbon dioxide is the most important of those, and we have a way of incorporating carbon dioxide, turning it into syngas and incorporating that into the alcohols without using Fischer-Tropsch. And it's an alternative PTL technology, effectively, and it will be covered by the new certification which we're striving for. On the other hand, standalone, you have a lot of flexibility. So you're not so tied in with the upstream suppliers, and you have some ability to switch feedstocks depending upon market conditions. I know there's a lot of considerations which go into that, but the possibility is at least there. And at the end of the day, the results of the study showed that integrate or segregate both work, and it's just really a question of circumstances.
Thank you very much, Andrew. I think we are very, very late. It's the time to finish this session. Thank you to all participants for attending this session on biofuels. Thank you to the speaker, great presentation, and the panelists. The presentation will be able on the BioFit website. I hope send all the presentation. And tomorrow, just as Stephanie said, 8:30, I think, start the policy breakfast retrofit for 55, moderated by Dina Bajkowski and Rainer Jassen. So don't miss it, please. See you tomorrow. And that's all from my part. Thank you very much.
Thank you very much.
Thank you.
Thank you very much.
you.
Have a nice afternoon.
Everybody.
Bye.
Thank you, everyone.
Bye.